In a single moment, 13.8 billion years ago, everything that ever was, is, or could be burst into existence from a point smaller than the period at the end of this sentence. We think of history as the rise and fall of civilizations, the march of human progress across mere thousands of years. But what if I told you that you are living in just one fleeting chapter of the greatest story ever told? A story that began with the birth of space and time itself, unfolded through cosmic dark ages and stellar explosions, witnessed the formation of galaxies and the emergence of life, and continues to write itself at this very moment as you watch these words. What is the complete story of everything? How did we journey from absolute nothingness to a universe filled with 1 trillion galaxies, each containing billions of stars, at least one of which harbors a planet where conscious beings can contemplate their own cosmic origins? Join me as we embark on the ultimate journey through time, from the first moment of creation to the far future of the cosmos, tracing the unbroken chain of events that led from the Big Bang to you, sitting here right now, about to discover your place in the grandest narrative of all. Before we begin this cosmic voyage, I'd love to know, what corner of the world are you joining me from, and what time is it where you are? Drop your location and local time in the comments below. It's fascinating to think that no matter when or where you're watching this, we're all traveling together through space on this pale blue dot, 67,000 miles per hour. Picture this: every atom in your body, every star in the night sky, every galaxy stretching to the edge of the observable universe, all of it once occupied a space so impossibly small that it defies human comprehension. We're talking about a point of infinite density and temperature called a singularity, where the normal laws of physics break down like a computer program encountering a fatal error. This wasn't an explosion in space, it was the explosive birth of space itself. Time didn't exist before this moment, because there was no before. The very concept of duration, of one moment following another, began with the Big Bang. It's like asking what's north of the North Pole. The question itself becomes meaningless. The four fundamental forces we know, today gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, incomprehensible superforce. Imagine a master key that could open every lock in the universe. Then think of that key shattering into 4 separate pieces, each with its own unique power. That's what happened as the universe cooled and expanded. Scientists like Stephen Hawking spent their entire careers trying to understand these first moments. And here's what's truly mind-bending. The mathematics suggests that quantum fluctuations, random variations in energy, might have created our universe from literally nothing. Not empty space, but actual nothingness. No space, no time, no matter, no energy. And yet, somehow, everything emerged. These aren't just abstract concepts dreamed up by theoretical physicists. The evidence for the Big Bang surrounds us. Every hydrogen atom in your body is a fossil from this primordial era, forged in the nuclear furnace of the universe's first minutes. The cosmic microwave background radiation, the afterglow of creation itself, still bathes every cubic centimeter of space, carrying the fingerprints of that first moment when our universe was 1,000,000 times hotter than the core of the sun. But here's where the story gets even stranger. Recent discoveries suggest our Big Bang might not have been the beginning of everything, but rather one event in an eternal cosmic process. Some theories propose that we live in a multiversine infinite collection of universes, each with its own Big Bang, its own laws of physics, its own story. If that's true, then what we call everything might be just one note in an infinite symphony of creation. The Planck epoch ended when gravity separated from the other forces, marking the end of the universe's first moment and setting the stage for the next incredible phase of cosmic evolution. What happened next defies every intuition you have about how things move and grow. In less time than it takes light to cross a proton, our universe underwent a period of expansion so rapid, so violent, that it makes every explosion you've ever imagined look like a gentle breeze. This is cosmic inflation, and it's the reason you exist. Imagine a balloon the size of a pinpoint, suddenly inflating to the size of a basketball, but this happened in 10 to the negative 35 seconds. During inflation, space itself expanded faster than the speed of light. Now, before you object and cite Einstein's speed limit, remember, Nothing can move through space faster than light, but space itself can expand at any rate it pleases. It's like being on a treadmill that's accelerating faster than you can run. You're not breaking any rules, but you're moving backward relative to your destination. This period of inflation, driven by a mysterious energy field called the inflaton, solved several profound puzzles that had been haunting cosmologists. Why is the universe so uniform in temperature when regions that have never been in contact share the same properties? Inflation explains this. These distant regions were once close neighbors before being stretched apart faster than light could travel between them. Think of it like this. Imagine you and a friend are standing next to each other on a football field, both wearing identical red shirts. Suddenly, the field starts expanding so rapidly that within seconds, you're separated by millions of miles. An alien observer might wonder why two people so far apart happen to be wearing the same color, but you'd know it's because you started together. Alan Guth, the physicist who first proposed inflation in 1980, called it the ultimate free lunch. Why? Because inflation didn't just stretch existing space, it created new space, and with it, new energy. The expanding universe actually generated the matter and energy that would later form galaxies, stars, and planets. The energy required to create all the matter in the observable universe. Essentially zero, thanks to the negative gravitational energy that exactly balances the positive mass energy. But inflation did something even more remarkable. It took quantum fluctuations, random variations in the energy field, and stretched them to cosmic proportions. These microscopic ripples became the seeds of every structure we see today. The slight variations in density that would eventually collapse under gravity to form the first stars and galaxies began as quantum uncertainties in the inflation field. Imagine shaking a bedsheet covered in tiny wrinkles, then stretching it until it's the size of a continent. Those tiny wrinkles would become mountain-sized variations in the fabric. That's essentially what inflation did to the quantum foam of the early universe, creating a cosmic blueprint for everything that would follow. The evidence for inflation is written across the sky in the cosmic microwave background. Satellites like WMAP and Planck have measured these ancient fluctuations with extraordinary precision, confirming predictions made decades before the technology existed to test them. We can literally see the shadows of quantum events that occurred when the universe was smaller than an atom. Inflation ended as suddenly as it began, when the inflaton field decayed and transferred its energy to ordinary matter and radiation. This moment, called reheating, marked the transition from the bizarre, quantum-dominated early universe to the more familiar epoch of hot, dense plasma that would eventually cool into the cosmic microwave background. As the universe emerged from inflation, it was about the size of a grapefruit, filled with an incredibly hot, dense soup of fundamental particles and radiation. The stage was now set for the next chapter in cosmic evolution, where the basic forces and particles we know today would finally take their familiar forms. As our grapefruit-sized universe continued to expand and cool, something extraordinary happened. The unified superforce that had governed reality began to shatter, like a perfect crystal breaking along natural fault lines under stress. First to separate was gravity, the weakest but most far-reaching of all forces. Even today, gravity is so feeble that the electromagnetic force in a simple refrigerator magnet can overcome the gravitational pull of the entire Earth. Yet gravity would ultimately sculpt the large-scale structure of the universe, gathering matter into the cosmic web of galaxies and clusters we see today. As temperatures dropped to a mere billion-trillion degrees, still incomprehensibly hot, but cool enough for the next phase transition, the strong nuclear force split away from the electro-weak force. The strong force, which would later hold atomic nuclei together, became the cosmic glue that would eventually allow complex atoms to exist. Finally, when the universe cooled to around 1 trillion degrees, the electromagnetic force separated from the weak nuclear force. This moment was crucial. Electromagnetic force would govern the behavior of charged particles and light itself, while the weak force would control certain types of radioactive decay, playing a vital role in stellar nucleosynthesis. These weren't just academic distinctions. Each force separation released enormous amounts of energy and fundamentally changed how matter and energy could interact. It was like watching a single musical instrument split into an entire orchestra, each section now capable of playing its own unique part in the cosmic symphony. With the four fundamental forces now distinct, the universe had acquired the basic rules of physics that still govern reality today. The stage was set for matter to begin its long journey toward complexity. Here's one of the most profound mysteries in all of physics. Why do you exist? According to our best understanding of particle physics, the Big Bang should have created equal amounts of matter and antimatter. When these two meet, they annihilate each other in a flash of pure energy, leaving behind only photons. If the universe had been perfectly symmetric, matter and antimatter should have completely destroyed each other, leaving behind a cold, empty cosmos filled with nothing but light. Yet here you are, made of matter, surrounded by a universe built from matter. Every atom in your body, every star in the sky, every planet and moon and grain of cosmic dust all matter, with barely a trace of antimatter to be found. Something broke the symmetry, and that asymmetry is the reason complexity, life, and consciousness could eventually emerge. The solution to this puzzle lies in a subtle violation of one of physics' most cherished principles, CP symmetry, which states that the laws of physics should remain the same if you swap matter for antimatter and flip spatial coordinates like a mirror image. In 1967, physicist Andrei Sakharov proposed that for matter to dominate our universe, three conditions must have been met: baryon number violation, CP violation, and departure from thermal equilibrium. During the first microsecond after the Big Bang, when temperatures exceeded 10 trillion degrees, these conditions were met. Certain interactions involving particles called X-boson hypothetical particles that exist only in grand unified theories could create slightly more matter than antimatter. We're talking about an incredibly tiny imbalance. For every billion antimatter particles, there were 1,000,000,001 matter particles. When the Great Annihilation began, those billion pairs of particles destroyed each other in brilliant flashes of gamma radiation. But that single leftover particle of matter own part in 1,000,000,000 survived. This cosmic remainder became the foundation for everything we see today. Every atom in your body is descended from these survivors of the primordial war between matter and antimatter. Think about the precision required for this to work. Too little asymmetry, and all matter and antimatter would have annihilated, leaving only radiation. Too much asymmetry, and the universe might have been so dominated by matter that it would have quickly collapsed under its own gravity. The balance was perfect, just enough asymmetry to leave behind the raw materials for stars, planets, and life. This matter-antimatter asymmetry represents one of the deepest unsolved problems in physics. While we can observe the consequences everywhere we look, we still don't fully understand the mechanism that created it. Experiments at the Large Hadron Collider and other facilities continue searching for clues about how this cosmic coin flip was rigged in favor of matter. The antimatter that once dominated half the universe didn't vanish entirely. Tiny amounts are still produced by cosmic ray interactions and radioactive decay. In fact, your body produces a few thousand antimatter particles every day through natural radioactive processes. These particles quickly encounter their matter counterparts and annihilate, but their brief existence connects you directly to the primordial battle that shaped our cosmos. As the universe continued to expand and cool, the surviving matter particles began to combine in new ways, setting the stage for the next crucial phase of cosmic evolution. For 380 years after the Big Bang, the universe was opaque. Light couldn't travel more than a few inches before colliding with a free electron or proton in the dense, hot plasma that filled all of space. If you could somehow travel back to this era and open your eyes, you wouldn't see anything, not because there was no light, but because light was trapped, constantly scattered and absorbed by the fog of ionized particles. But then, as the universe continued to expand and cool, something miraculous happened. When temperatures dropped to about 30 Kelvin, still hot enough to melt copper, but cool enough for a fundamental phase, transition electrons and protons began to combine into neutral hydrogen atoms for the first time. This moment, called recombination, was like watching fog lift from a valley at sunrise. Suddenly, light could travel freely through space. The universe became transparent, and the first photons began their epic journey across the cosmos. This was the moment when the cosmic microwave background was born, the afterglow of creation itself. Imagine being in a room filled with thick smoke. unable to see anything beyond your fingertips. Then, in an instant, the smoke clears, and you can see to the horizon. That's what happened to the universe during recombination, except the room was the entire cosmos, and the horizon was the edge of space itself. These liberated photons carry with them a baby picture of the universe, a snapshot taken when cosmic history was just beginning. Originally, this light was intensely bright and hot, with a temperature of 30 Kelvin, glowing with the warm orange light of recombination. But as the universe expanded over the following 13.8 billion years, this light was stretched and cooled, its wavelength increasing, and its temperature dropping to just 2.7 Kelvin, above absolute zero. Today, this ancient light bathes every cubic centimeter of space as microwave radiation. It's incredibly faint, about 100 billion times dimmer than the light from a candle, but it's everywhere. Right now, as you read these words, trillions of these ancient photons are passing through your body every second, cosmic messengers carrying information from the universe's infancy. The discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson was one of the greatest accidental discoveries in the history of science. Working at Bell Labs, they were trying to eliminate a persistent noise in their radio antenna that seemed to come from everywhere in the sky. No matter which direction they pointed their equipment, no matter what time of day or season, the signal was always there. They even thought it might be caused by pigeon droppings in their antenna and spent considerable effort cleaning it out. What they had discovered was the echo of creation itself. But the cosmic microwave background revealed much more than just proof of the Big Bang. When satellites like COBE, WMAP, and Planck mapped this radiation with extraordinary precision, they found something remarkable: tiny fluctuations in temperature across the sky, variations of just a few millionths of a degree. These fluctuations weren't random noise, they were the shadows of quantum events that occurred during inflation, stretched to cosmic scales. These temperature variations correspond to regions of slightly different density in the early universe. The slightly cooler regions had slightly more matter, while the warmer regions had slightly less. Under the influence of gravity, the denser regions would eventually collapse to form the first stars and galaxies, while the less dense regions would become the cosmic voids we see today. In essence, the cosmic microwave background is a map of the universe's destiny, written when it was just 380 years old. Every galaxy cluster, every cosmic web filament, every vast empty space in today's universe can be traced back to these primordial fluctuations. The supermassive black hole at the center of our galaxy, the local group of galaxies we belong to, even the specific location where the solar system would eventually form of it, was predetermined by the quantum ripples visible in the cosmic microwave background. The precision of these measurements has allowed cosmologists to determine the age of the universe, 13.8 billion years. Its composition, roughly 5% ordinary matter, 25% dark matter, and 70% dark energy, and its ultimate fate. We can literally read the universe's biography in this ancient light. As we look deeper into the cosmic microwave background, we're also looking deeper into the mystery of existence itself. Some theoretical physicists suggest that these patterns might contain evidence of parallel universes or cosmic collisions that occurred before our Big Bang. Others propose that the subtle polarization patterns in this radiation might reveal the gravitational wave signatures of inflation itself. The cosmic microwave background represents the moment when the universe transitioned from its violent, opaque infancy to the transparent cosmos we inhabit today. With light finally free to travel through space, the stage was set for the next great chapter in cosmic evolution, the Dark Age, a period of profound change that would ultimately lead to the birth of the first stars. After the brilliant flash of recombination faded, the universe entered its longest and most mysterious epoch, the cosmic Dark Age. For hundreds of millions of years, there were no stars, no galaxies, no sources of light except the fading glow of the cosmic microwave background, slowly redshifting from visible light into the infrared and beyond. Picture the universe during this era, vast, dark, and seemingly empty, filled only with neutral hydrogen and helium gas drifting through space at temperatures barely above absolute zero. If you could somehow travel back to this time, you would find yourself in absolute darkness, surrounded by invisible clouds of gas so thin that even the best vacuum chambers on Earth are dense by comparison. Yet this was not a time of cosmic stagnation. Hidden in the darkness, momentous changes were taking place. The tiny density fluctuations imprinted in the cosmic microwave background were beginning to grow under the influence of gravity. Regions that were slightly denser than average began to pull in more matter, becoming denser still, while less dense regions became relatively emptier. This was gravity's slow, patient work. Unlike the violent explosions and rapid phase transitions of the first moments after the Big Bang, the Dark Age was characterized by gradual, inexorable change. Invisible dark matter, comprising most of the universe's mass, was already beginning to form the cosmic scaffolding upon which all future structure would be built. The first structures to emerge were dark matter, halos, invisible gravitational wells that would later become the foundations for galaxies. These halos grew through a process cosmologists call hierarchical structure formation, where smaller structures merge to form larger ones, like tributaries joining to form rivers, and rivers flowing into seas. During this era, the universe was cooling steadily as it expanded. The temperature of space itself dropped from thousands of degrees to just a few degrees above absolute zero. The hydrogen and helium gas that filled the universe was neutral electrons, were bound to atomic nuclei, unable to absorb or emit light efficiently. This is why the Dark Age was truly dark. There were virtually no processes that could produce visible light. But within the growing dark matter halos, something important was happening. Gas was beginning to fall into these gravitational wells, heating up as it did so. The kinetic energy of infalling matter was converted to thermal energy, warming the gas clouds that would eventually collapse to form the first stars. The Dark Age was also when the universe's chemical composition was locked in. The light element hydrogen, helium, and trace amounts of lithium had been forged in the nuclear furnace of the Big Bang's first few minutes. No heavier elements existed yet. There was no carbon, no oxygen, no iron, no silicon. The periodic table contained only its first few entries, waiting for the nuclear fusion factories of the first stars to begin producing the elements that would eventually make planets and life possible. This period represents one of the most challenging frontiers in modern astronomy. Because no light sources existed, we cannot directly observe the Dark Age with conventional telescopes. It's like trying to study a forest by looking only at the roots underground. We must infer what happened from its consequences. However, astronomers are developing ingenious ways to probe this hidden era. Radio telescopes are searching for the faint 21-centimeter radiation emitted by neutral hydrogen, hoping to map the distribution of gas during the Dark Age. Future space-based observatories may be able to detect the gravitational wave signatures of the first dark matter structures forming. The James Webb Space Telescope is already pushing back the boundaries of the observable universe, detecting galaxies that formed when the cosmos was less than 400 million years old. Galaxies whose light has traveled more than 13 billion years to reach us. These observations are revealing the tail end of the Dark Age, showing us the universe just as the first stars were beginning to ignite. As the Dark Age progressed, the stage was being set for one of the most important transitions in cosmic history. Deep within the growing dark matter halos, gas clouds were reaching the critical temperatures and densities needed for nuclear fusion. The universe was pregnant with potential, waiting for gravity to compress the first hydrogen clouds beyond a crucial threshold. The darkness was about to end. But first, we need to understand the invisible architecture that made the birth of the first stars possible. Everything you can see, every star, every galaxy, every planet, every atom in your body represents less than 5% of the universe. The other 95% is invisible, detectable only through its gravitational effects on the ordinary matter we're familiar with. This invisible majority is composed of dark matter and dark energy, and during the cosmic Dark Age, dark matter was busy constructing the hidden framework upon which all visible structure would eventually hang. Dark matter is perhaps the most humbling discovery in the history of science. Here we are, conscious beings made of atoms, living on a rocky planet, orbiting a nuclear-powered star, thinking we understand the universe, only to discover that we're made of the cosmic equivalent of foam on the oceana, tiny minority component floating on an invisible sea. The story of dark matter's discovery reads like a cosmic detective novel. In the 1930s, astronomer Fritz Zwicky was studying the Coma cluster of galaxies when he noticed something strange. The galaxies were moving so fast that they should have escaped the cluster's gravitational pull long ago. It was like watching cars race around a circular track at such high speeds that they should fly off into space, yet somehow they remained bound to their circular paths. Zwicky calculated that the cluster must contain about 10 times more mass than he could see in stars and gas. He called this missing mass Dunkel Materia, dark matter. For decades, most astronomers dismissed this as an error in calculation or an exotic property of gravity we didn't yet understand. But the evidence kept mounting. In the 1970s, Vera Rubin's observations of spiral galaxies revealed the same phenomenon. Stars in the outer regions of galaxies were orbiting much too fast to be held in place by the gravitational pull of visible matter alone. The rotation curves of galaxies were flat rather than declining with distance, indicating the presence of vast halos of invisible mass. Today, we know that dark matter particles were the first structures to form in the universe. Unlike ordinary matter, dark matter doesn't interact electromagnetically. It doesn't absorb, emit, or scatter light. This means that during the era when ordinary matter was still trapped in the cosmic fog, dark matter was already free to respond to gravitational forces and begin clumping together. Think of it this way. While ordinary matter was like paint mixed with water, flowing smoothly and unable to form distinct structures, dark matter was like oil drops in that same waterable to separate, coalesce, and form distinct concentrations, despite being surrounded by the flowing medium of ordinary matter and radiation. Computer simulations of dark matter evolution reveal a breathtaking cosmic architecture. Dark matter forms a vast web-like structure, spanning the entire universe, the cosmic web. Dense filaments of dark matter connect massive nodes, where galaxy clusters will eventually form, while vast empty regions called voids stretch between the filaments like bubbles in cosmic foam. This dark matter web serves as the invisible skeleton of the universe. When ordinary matter was finally released from the radiation fog during recombination, it fell into the gravitational wells already carved out by dark matter. The densest concentrations of dark matter became the sites where the first stars would form, while the cosmic web filaments became the highways along which matter would flow to build the first galaxies. The scale of this hidden architecture is staggering. Dark matter halos can extend far beyond the visible boundaries of galaxies. Our own Milky Way is embedded in a dark matter halo that extends perhaps 300 light-years from the galactic center, 3 times the diameter of the visible galaxy. This invisible halo contains about 10 times more mass than all the stars and gas we can see. But what is dark matter made of? This remains one of the deepest mysteries in physics. It's not made of atoms, because atomic matter would interact with light and radiation in ways we can detect. Leading candidates include exotic particles like WIMPs, weakly interacting massive particles, or axion hypothetical particles that would interact with ordinary matter only through gravity and possibly the weak nuclear force. Underground laboratories around the world are searching for these elusive particles. Detectors buried deep beneath mountains, shielded from cosmic rays and background radiation, wait for the rare collision between a dark matter particle and an atomic nucleus. So far, dark matter has lived up to its name, remaining frustratingly invisible to our most sensitive instruments. Some scientists have proposed alternative explanations, suggesting that our understanding of gravity itself might be incomplete. Modified theories of gravity attempt to explain galactic rotation curves and cosmic structure without invoking invisible matter. But the overwhelming evidence from gravitational lensing, cosmic microwave background observations, and computer simulations of structure formation all point to the existence of dark matter. During the cosmic dark age, dark matter was doing the heavy lifting, literally. While ordinary matter remained largely smooth and uniform, dark matter was already building the gravitational potential wells that would eventually become galaxies. The first dark matter halos to collapse were relatively small, with masses perhaps 1,000,000 times that of our Sun. These mini-halos would later merge to form the larger structures we see today. The interaction between dark matter and ordinary matter during this era was subtle but crucial. As gas fell into dark matter halos, It was heated by the gravitational potential energy released during infall. In the densest regions, this heating eventually reached the temperatures necessary for nuclear fusion. The stage was set for the cosmic dark age to end in the most spectacular way possible. The invisible architecture was complete. The cosmic web was in place. Deep within the first dark matter halos, hydrogen and helium gas clouds were growing denser and hotter, approaching the critical threshold, where nuclear fire would ignite for the first time in cosmic history. In the depths of cosmic darkness, after hundreds of millions of years of patient waiting, something extraordinary was about to happen. Deep within the densest dark matter halos, clouds of primordial hydrogen and helium gas had been falling inward, heating up, growing denser, until they reached a critical threshold that would change the universe forever. The first star was about to be born. These weren't the yellow, sun-like stars we see today. The first generation of stars what astronomers call population 3 stars were monsters beyond imagination. Without heavy elements to help cool collapsing gas clouds, these primordial stellar nurseries could only fragment into very massive objects. We're talking about stars with masses 50, 100, even 200 times that of our Sun, burning with the intensity of millions of solar furnaces. Picture this moment: a gas cloud roughly the size of our solar system, containing nothing but hydrogen and helium left over from the Big Bang, collapsing under its own gravity. As it contracted, gravitational potential energy converted to heat, warming the cloud to thousands of degrees. But unlike modern star formation, there were no dust grains or heavy elements to radiate away this heat efficiently. The cloud continued to collapse, its core growing denser and hotter, until finally, at temperatures of 10 million degrees, hydrogen nuclei began to fuse into helium. Nuclear fusion, the same process that powers our Sun, ignited for the first time in cosmic history. The universe's first star burst into brilliant life, ending the cosmic dark age with a flood of ultraviolet light. These first stars were not just bright, they were apocalyptic. A typical population 3 star would have burned with the luminosity of several million suns, its surface temperature reaching 50 degrees Celsius, hot enough to appear blue-white and emit intense ultraviolet radiation. If you could somehow place one of these stellar behemoths where our Sun is today, it would appear 20 times brighter and would strip away Earth's atmosphere in a matter of hours. But their brilliance came at a cost. These massive stars burned through their nuclear fuel at an incredible rate. While our Sun will shine for 10 billion years, the first stars exhausted their fuel in just a few million years, a cosmic eye blink. They lived fast and died young, their brief lives playing out like stellar fireworks against the cosmic darkness. The impact of these first stars extended far beyond their immediate neighborhoods. Their intense ultraviolet radiation began to ionize the neutral hydrogen gas that filled the universe, creating expanding bubbles of ionized plasma around each star. This process, called reionization, gradually transformed the universe from a neutral, opaque medium back into an ionized, transparent one, though this time, instead of being opaque due to density and temperature, as in the early universe, the opacity had been due to neutral atoms absorbing specific wavelengths of light. Think of it like cities lighting up across a dark continent. Each first star was like a powerful beacon, illuminating its surroundings and pushing back the darkness. As more stars ignited, their ionization bubbles grew and eventually overlapped, creating vast regions where hydrogen was once again ionized, just as it had been in the first 380 years after the Big Bang. But the first stars did something even more important. They began the process of cosmic chemical evolution. In their incredibly hot cores, temperatures reached hundreds of millions of degrees, hot enough to fuse not just hydrogen into helium, but helium into carbon, carbon into oxygen, oxygen into silicon, and silicon into iron. For the first time in cosmic history, the universe was manufacturing elements heavier than lithium. These stellar furnaces operated on a scale that's difficult to comprehend. A single population 3 star could produce more heavy elements in its brief lifetime than 1,000 sun-like stars combined. The nuclear reactions in their cores followed a complex chain of fusion processes, building up the periodic table one nuclear collision at a time. The most massive of these first stars faced an extraordinary fate. When they exhausted their fuel, they didn't die quietly like smaller stars. Instead, they collapsed catastrophically and exploded as supernovae, but not just any supernovae. These were hypernovae, explosions so energetic they could outshine entire galaxies and scatter their newly forged heavy elements across vast regions of space. Some of the most massive population 3 stars may have skipped the supernova phase entirely, collapsing directly into black holes. These primordial black holes would become the seeds around which the first galaxies formed, eventually growing into the supermassive black holes we find at the centers of galaxies today. The death of each first star was as important as its birth. The heavy elements created in stellar coarse carbon, oxygen, silicon, iron, and dozens of others were blasted into space by supernova explosions. For the first time, the universe contained the raw materials necessary for rocky planets and, eventually, life. This cosmic enrichment process was incredibly inefficient at first. The heavy elements ejected by dying stars were diluted across vast volumes of space, mixed with the primordial hydrogen and helium that still dominated the universe's composition. It would take many cycles of star birth, life, and death to build up significant concentrations of heavy elements. But the process had begun. The universe was no longer composed solely of the light elements forged in the Big Bang. Carbon atoms, the backbone of organic chemistry, existed for the first time. Oxygen atoms, essential for water and respiration, began their cosmic journey. Iron atoms, crucial for planetary cores and biological processes, started accumulating in the interstellar medium. The first stars had broken the cosmic deadlock. They had ended the Dark Age, begun the reionization of the universe, and started the long process of chemical evolution that would eventually make complex chemistry, planets, and life possible. The universe would never be the same. Inside the core of a massive first-generation star, temperatures soared to hundreds of millions of degrees, creating conditions that hadn't existed since the first moments after the Big Bang. But this time, instead of the chaotic particle soup of the primordial universe, nuclear fusion was proceeding in an orderly, step-by-step process that would build the foundation of all future complexity. The story of element creation, what astronomers call nucleosynthesis, one of the most elegant processes in nature. It begins simply: 4 hydrogen nuclei fuse together to create one helium nucleus, releasing tremendous amounts of energy in the process. This is the same fusion reaction that powers our Sun, but in the cores of population 3 stars, it proceeded at an incredible rate due to their extreme temperatures and densities. But helium fusion requires even higher temperatures than hydrogen fusion, about 100 million degrees. When the first stars exhausted their hydrogen fuel in their cores, they faced a crisis. Nuclear fusion temporarily stopped, and without the outward pressure of radiation to support them, their cores began to collapse under their own immense gravity. This collapse was exactly what the universe needed for the next step in cosmic evolution. As the stellar core contracted, it heated up even more, eventually reaching the temperatures necessary for helium fusion. 3 helium nuclei combined to form carbonth, first heavy element produced by stellar fusion, and arguably the most important element for the future of the universe. Carbon is special. Its atomic structure allows it to form 4 chemical bonds, making it the basis for complex organic molecules. Every carbon atom in your body was forged in the core of a dying star billions of years ago. Carl Sagan wasn't being poetic when he said we are made of star stuff. We are literally built from the ashes of stellar furnaces. But the nucleosynthesis process didn't stop with carbon. As the massive first stars continued to evolve, their cores developed a layered structure like a cosmic onion. The outermost layer still fused hydrogen into helium. Deeper in, helium fused into carbon. Deeper still, carbon fused into oxygen. Each layer required higher temperatures and densities, creating a sequence of nuclear burning phases that built up the periodic table element by element. Silicon burning, the final stage of nuclear fusion in stellar cores, produced iron element 26 on the periodic table, but iron represents a nuclear dead end. Unlike lighter elements, fusing iron nuclei together doesn't release energy, it actually absorbs energy. When a stellar core fills up with iron, nuclear fusion can no longer provide the pressure needed to prevent gravitational collapse. What happened next was catastrophic and beautiful. The iron core collapsed in less than a second, creating conditions so extreme that protons and electrons were crushed together to form neutrons. The infalling outer layers of the star bounced off this incredibly dense neutron core, creating a shockwave that ripped through the star at 30 kilometers per second. This was the first supernova explosion in cosmic history, stellar death so violent that it briefly outshone the rest of the universe combined. But even more important than the explosion itself was what happened during those first few seconds. In the incredibly hot, dense environment of the supernova shockwave, elements heavier than iron were created for the first time through rapid neutron capture processes. Gold, silver, platinum, uranium, these elements that we consider precious and exotic, were born in the nuclear furnace of dying stars. The gold in your jewelry, the silver in your electronics, the uranium that powers nuclear reactors, all of it was created during the violent deaths of the first generation of stars. The supernova explosions scattered these newly created elements across thousands of light-years of space, mixing them with the primordial hydrogen and helium that still dominated the universe. This cosmic recycling process ensured that the next generation of stars would form from gas clouds enriched with heavy elements, allowing for the formation of smaller, longer-lived stars more like our Sun. The efficiency of this enrichment process was remarkable. A single massive population 3 star could produce and distribute more heavy elements than would be created by thousands of smaller stars over billions of years. These first stellar deaths seeded vast regions of space with the raw materials for planets, asteroids, and eventually life itself. But the legacy of the first stars extended beyond just chemical enrichment. The energy from their supernova explosions carved out vast bubbles in the interstellar medium, creating shock waves that triggered the formation of new stars from the compressed gas at the bubble edges. They also heated the surrounding gas to millions of degrees, creating the first hot interstellar medium and laying the groundwork for galactic evolution. As the universe entered its second billion years, it was a fundamentally different place than it had been during the cosmic dark age. Light blazed from countless stars, heavy elements drifted through space in expanding supernova remnants, and the stage was set for the next great phase of cosmic evolution, the formation of the first galaxies. Imagine the universe as a vast city under construction, where individual lights, the first starshave, begun to flicker on across the cosmic landscape. But these weren't randomly scattered streetlights. They were gathering into neighborhoods, districts, and eventually entire metropolitan areas of light. The first galaxies were being born. By the time the universe was 1 billion years old, gravity had been working patiently for eons to gather stars into larger and larger associations. What started as individual massive stars burning in isolation gradually evolved into small groups, then clusters, then the sprawling stellar cities we call galaxies. The first galaxies were nothing like the majestic spiral galaxies we see today. These early galactic pioneers were small, irregular, and chaotic, more like stellar villages than cosmic metropolises. They formed through a process astronomers call hierarchical assembly, where smaller structures constantly merged to form larger ones, like streams flowing together to form rivers, and rivers joining to create great waterways. Picture this cosmic construction process. Small dark matter halos, each containing perhaps a few million solar masses, begin to merge under their mutual gravitational attraction. As they combine, their associated gas clouds collide and compress, triggering intense bursts of star formation. These early galaxies were star formation factories, converting gas into stars at rates hundreds of times faster than modern galaxies. The James Webb Space Telescope has given us our first clear glimpse of these ancient galactic nurseries, and they're full of surprises. Galaxies that formed when the universe was less than 600 million years old are already surprisingly massive and well-organized. Some contain supermassive black holes that seem impossibly large for such young systems, challenging our understanding of how quickly these cosmic monsters could grow. These early galaxies were also incredibly bright for their size. Without the heavy elements that allow modern stars to form with a wide range of masses, the first galactic generations were dominated by massive, luminous stars that burned hot and blue. A typical early galaxy might contain only 1% of the stars in today's Milky Way, yet shine nearly as brightly due to the extreme nature of its stellar population. The process of galaxy formation was violent and chaotic. Computer simulations show these early systems constantly merging, disrupting each other's structure and triggering massive starbursts in the process. It was like watching cities being built and destroyed in fast forward, with new structures constantly rising from the rubble of their predecessors. But perhaps most importantly, these first galaxies were beginning to organize matter on truly cosmic scales. For the first time since the Big Bang, significant amounts of mass were being concentrated into relatively small regions of space. This concentration created the gravitational wells that would eventually grow into the galaxy clusters and superclusters we see today. The formation of galaxies also marked the beginning of cosmic chemical evolution on a grand scale. Each generation of stars within these early galaxies lived, died, and enriched the interstellar medium with heavy elements. Gradually, the primordial composition of pure hydrogen and helium gave way to a more complex mixture that included carbon, oxygen, silicon, and iron. This chemical enrichment was crucial for the future of the universe. Heavy elements allowed gas clouds to cool more efficiently, making it possible for smaller, longer-lived stars to form. They also made possible the formation of dust grains, which would later provide the building blocks for planets. The first galaxies were cosmic alchemical laboratories, transforming simple hydrogen and helium into the full spectrum of elements we find in the modern universe. The most massive of these early galaxies became the ancestors of today's giant elliptical galaxeous cosmic cities that can contain 1 trillion stars. But even the smallest early galaxies played a crucial role in cosmic evolution. Many were eventually incorporated into larger systems through galactic mergers, contributing their stars and heavy elements to build the diverse galaxy population we see today. By the end of the universe's first billion years, the cosmic landscape had been transformed. What had once been a dark, nearly empty space was now illuminated by millions of small galaxies, each a beacon of nuclear fire in the cosmic night. These stellar cities were beginning to interact gravitationally, setting the stage for even grander structures to emerge. The first galaxies had established the basic pattern that would govern cosmic evolution for the next 12 billion years, gravity gathering matter into ever larger structures, while nuclear fusion in stellar cores continued the patient work of building up the periodic table element by element. The cosmic dark age was truly over, replaced by an era of light, structure, and increasing complexity. In the hearts of the first galaxies, something even more dramatic than star formation was taking place. Supermassive black holes, gravitational monsters, containing millions or billions of times the mass of our sun, were beginning to stir to life, fundamentally altering the evolution of their host galaxies and the universe itself. The origin of these cosmic titans remains one of astronomy's greatest mysteries. How do you create a black hole with the mass of 1 billion suns when the universe is less than 1 billion years old? The math is staggering. Even if these objects started as the collapsed remnants of the first massive stars and grew as fast as physically possible by accreting matter, there simply wasn't enough time for them to reach the enormous sizes we observe. Some of these supermassive black holes must have formed through more exotic processes. Perhaps they began as intermediate mass black holes created by the direct collapse of massive gas clouds in the early universe. Or maybe they formed from the mergers of multiple stellar mass black holes in the dense environments of the first star clusters. The details remain hotly debated, but the evidence is clear. By the time the universe was just a few 100 million years old, supermassive black holes were already fully grown and active. When matter falls into a supermassive black hole, it doesn't simply disappear quietly. Instead, it forms a swirling accretion disk, heating up to millions of degrees through friction and magnetic forces. This superheated matter glows brilliantly across the electromagnetic spectrum, creating some of the most luminous objects in the universe, quasars. The first quasars were cosmic lighthouses, visible across billions of light-years of space. A single active supermassive black hole could outshine its entire host galaxy by factors of hundreds or thousands. These weren't just bright lights. They were cosmic engines of incredible power, converting matter into energy with an efficiency that makes nuclear fusion look wasteful. But quasars did more than just shine. They launched powerful jets of particles at nearly the speed of light, stretching for thousands of light-years beyond their host galaxies. These jets carried enormous amounts of energy and momentum, capable of heating and dispersing gas across vast regions of space. For the first time in cosmic history, individual objects could influence their environment on truly galactic scales. This had profound consequences for galaxy evolution. The energy output from active supermassive black holes could halt star formation by heating the surrounding gas to temperatures too high for gravitational collapse. It was as if each galaxy contained a thermostat that could regulate its own growth, preventing it from converting all its gas into stars too quickly. The relationship between supermassive black holes and their host galaxies appears to be symbiotic. Observations of nearby galaxies reveal a tight correlation between black hole mass and various galaxy properties, such as the mass of the central stellar bulge. This suggests that galaxies and their central black holes evolve together, each influencing the other's growth. During major galaxy mergers, the supermassive black holes at their centers would eventually spiral inward and merge, creating gravitational wave events of almost unimaginable power. These mergers would have sent ripples through space-time that we're only now learning to detect with instruments like LIGO and Virgo. The awakening of supermassive black holes marked a new phase in cosmic evolution. No longer were galaxies simple collections of stars held together by gravity. They had become complex ecosystems where stellar evolution, gas dynamics, and black hole activity all interacted in intricate feedback loops that determined how quickly galaxies could form stars and how large they could ultimately grow. Step back far enough from any galaxy, any cluster, any structure in the universe, and a breathtaking pattern emerges. What first appears as random scattered points of light resolves into something that looks remarkably like a vast neural network, or the intricate structure of a spider's web spanning the entire cosmos. This is the cosmic web, the largest structure in the universe, and one of the most beautiful. The cosmic web is the scaffolding upon which everything else in the universe hangs. Imagine the universe as a three-dimensional tapestry, woven from dark matter and ordinary matter, where brilliant galaxies and galaxy clusters mark the intersections of cosmic threads, while vast empty voids stretch between the filaments like bubbles in cosmic foam. This grand architecture began to form during the cosmic dark age, but it took billions of years for the pattern to become clearly visible. The process started with the tiny density fluctuations imprinted in the cosmic microwave background quantum ripples from the inflationary epoch that were stretched to cosmic proportions. These minuscule variations in density, just parts per million, were the seeds from which the largest structures in the universe would grow. Dark matter, being immune to electromagnetic forces, was the first to respond to these gravitational seeds. While ordinary matter remained coupled to radiation and couldn't clump efficiently, dark matter was free to collapse into the growing potential wells carved out by gravity. Computer simulations of dark matter evolution reveal how these initial fluctuations developed into an intricate network of filaments and nodes over billions of years. The formation of the cosmic web follows a predictable hierarchy. First, dark matter collapses into small halos. These halos then merge to form larger structures, which combine into larger structures still, and so on. It's like watching a river system form in reverse. Instead of large rivers branching into smaller tributaries, small streams combine to form increasingly larger waterways. The nodes where multiple filaments intersect became the sites of galaxy clusters, gravitationally bound collections of hundreds or thousands of galaxies. These clusters represent the largest gravitationally bound structures in the universe, containing as much mass as 1,000,000 billion suns. The Coma cluster, where Fritz Zwicky first discovered evidence for dark matter, is one such cosmic metropolis, home to over 1,0 galaxies bound together by gravity. Between the filaments stretch the cosmic voids, vast regions of space that are nearly empty of galaxies. These voids aren't completely empty. They contain some dark matter and gas, but their density is so low that they represent the closest thing to nothingness that exists in our universe. Some voids span hundreds of millions of light years across, so large that light from one edge would take longer to reach the other side than complex life has existed on Earth. The cosmic web isn't static. It's constantly evolving, as gravity continues its patient work. Filaments grow longer and denser, voids expand and empty out further, and clusters continue to accrete new members. This evolution happens slowly by human standards. Major changes occur over hundreds of millions or billions of years, but the process never stops. One of the most remarkable aspects of the cosmic web is its similarity to other complex networks found in nature. The large-scale structure of the universe bears an uncanny resemblance to neural networks in the brain, root systems of plants, and even the structure of the internet. This similarity isn't coincidental, it reflects fundamental principles of how complex systems organize themselves under the influence of competing forces. In the cosmic web's case, two forces compete: gravity, which tries to pull matter together, and the expansion of the universe, which tries to spread everything apart. The balance between these forces determines the final structure. Regions where gravity wins become filaments and clusters, while regions where expansion dominates become voids. The cosmic web also serves as the universe's plumbing system. Gas flows along the filaments like water through pipes, feeding growing galaxies with the raw materials for star formation. When galaxies collide and merge, they typically do so along filament directions, guided by the underlying dark matter structure. Observations of this cosmic architecture require surveying millions of galaxies across vast volumes of space. Projects like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies, revealing the cosmic web in stunning detail. These maps show filaments stretching across hundreds of millions of light-years, punctuated by dense nodes where galaxy clusters reside. But the cosmic web extends far beyond what we can see with optical telescopes. The bulk of its mass is in the form of dark matter, which we can only detect through its gravitational effects. Techniques like weak gravitational lensing allow astronomers to map the dark matter distribution by observing how it bends light from background galaxies. Recent observations have even detected the ordinary matter component of the cosmic web directly. Hot gas residing in the filaments between galaxies emits X-rays and can be observed with space-based telescopes. This warm, hot intergalactic medium contains a significant fraction of the universe's ordinary matter that was previously missing from our cosmic census. The cosmic web also plays a crucial role in galaxy evolution. A galaxy's position within the web structure, whether it sits in a dense filament, at a cluster node, or in a sparse void, strongly influences its properties. Galaxies in dense environments tend to be older, redder, and contain less gas for star formation, while galaxies in voids are typically younger, bluer, and more actively forming stars. Understanding the cosmic web is essential for understanding the universe's future. As dark energy accelerates cosmic expansion, the web will continue to evolve. Filaments will stretch and thin out, while voids will expand and dominate more of the universe's volume. Eventually, in the far future, the cosmic web may dissolve entirely as expansion overcomes gravity on all but the smallest scales. The cosmic web represents the universe's masterpiece of architectural engineering, a structure so vast and complex that we're only now beginning to appreciate its full scope and beauty. It's the stage upon which the entire cosmic drama unfolds, the framework that connects every star, every galaxy, and ultimately every atom in the universe into a single, interconnected whole. Between 2 and 4 billion years after the Big Bang, the universe reached its most productive period, cosmic golden age, when star formation peaked across the cosmos. During this era, galaxies were converting gas into stars at rates that dwarf anything we see in the modern universe, creating the stellar populations that would dominate cosmic history for the next 10 billion years. This wasn't just a slight uptick in stellar birth rates. It was a cosmic baby boom of unprecedented proportions. Galaxies during this epoch were forming stars at rates 10 to 100 times higher than typical galaxies today. If star formation were a factory production line, the early universe was running at full capacity with multiple shifts, while the modern universe operates at barely 10% efficiency. The reasons for this peak are written in the fundamental physics of cosmic evolution. By this time, the universe had expanded and cooled enough that gas could efficiently collapse into stellar nurseries, but it was still dense enough that galaxies contained vast reservoirs of pristine material for star formation. It was the Goldilocks zone of cosmic evolution. Conditions were just right for maximum stellar productivity. During this golden age, typical star-forming galaxies were converting millions of solar masses of gas into stars every year. To put this in perspective, our own Milky Way currently forms about 1 new star per year. These ancient galactic powerhouses were creating stellar populations at rates that would exhaust their gas supplies in just a few 100 million years if sustained. The stars born during this era weren't the massive, short-lived giants of the first generation. By now, several cycles of stellar birth, death, and chemical enrichment had created a universe where stars could form across the full range of masses we see today. This period marked the birth of the vast majority of long-lived, sun-like stars that populate galaxies throughout the modern universe. Think of it this way. If you could somehow catalogue every star in the observable universe and arrange them by age, you'd find that more stars were born during this relatively brief golden age than in all the billions of years since. The stellar census of the cosmos is dominated by these middle-aged stars, now 10 to 12 billion years old, that were forged during the universe's most productive epoch. The peak of star formation coincided with the peak era of galaxy mergers and interactions. As dark matter halos continued to grow and merge hierarchically, their associated galaxies were brought into close contact, triggering massive starbursts when gas clouds collided and compressed. These merger-driven starbursts could convert enormous amounts of gas into stars in just a few tens of millions of years. But this golden age contained the seeds of its own decline. The same processes that drove intense star formation also began to shut it down. Massive stars born during starbursts exploded as supernovae within just a few million years, heating and dispersing the surrounding gas. The collective energy from multiple supernovae could drive galactic-scale winds, blowing star-forming material out of galaxies entirely. Supermassive black holes at galactic centers also played an increasingly important role as they grew and became more active. The energy they released while accreting matter could heat gas to millions of degrees, preventing it from cooling and collapsing to form new stars. This created a cosmic thermostat effect. The more actively a galaxy formed stars, the more likely it was to trigger feedback processes that would shut down future star formation. The Golden Age also marked the transition from a universe dominated by actively star-forming galaxies to one increasingly populated by red and dead elliptical galaxies. These massive systems, formed through major mergers during this epoch, quickly exhausted their gas supplies and settled into a more quiescent state dominated by aging stellar populations. Galaxy clusters grew increasingly important during this period, as gravitational gathering grounds for cosmic evolution. Within these dense environments, galaxies experienced frequent interactions that could trigger starbursts but also strip away their gas supplies through ram pressure as they moved through the hot intracluster medium. The observational evidence for this golden age comes from deep surveys that look back in time by observing distant galaxies. The Hubble Space Telescope, and now the James Webb Space Telescope, can peer so far into the universe that they see galaxies as they were billions of years ago. These observations reveal a universe that was far more active and dynamic than today's relatively quiescent cosmos. By the end of this golden age, around 10 billion years ago, the fundamental character of the universe had shifted. The era of abundant, pristine gas and rapid star formation was giving way to a more mature cosmos, where stellar birth rates would steadily decline over the remaining billions of years of cosmic evolution. The stars born during this cosmic golden age would go on to become the dominant stellar population in most galaxies. Many of these stars are still shining today, having lived for 10 billion years or more. In a very real sense, we live in a universe illuminated primarily by the stellar legacy of this ancient productive epoch. By the end of the cosmic golden age, the universe had undergone a fundamental transformation that would make everything that followed possible, including you. Over billions of years and countless stellar generations, the pristine hydrogen and helium from the Big Bang had been processed through stellar cores and scattered by supernova explosions, gradually building up what astronomers call metals, every element heavier than helium. This terminology might seem confusing at first. To an astronomer, carbon is a metal, oxygen is a metal, even calcium and iron are metals. This isn't a mistake in chemistry. It's a reflection of cosmic perspective. In a universe that started with only hydrogen, helium, and traces of lithium, everything else represents the accumulated wealth of stellar alchemy. The process of cosmic chemical evolution follows a predictable pattern, but one that took billions of years to unfold. Early in cosmic history, the metallicity, the fraction of heavy elements in gas and stars, was essentially zero. The first stars had to forge heavy elements from scratch, working with nothing but the light elements left over from primordial nucleosynthesis. Each stellar generation built upon the work of its predecessors. When the first massive stars died in spectacular supernova explosions, they seeded their surroundings with newly created heavy elements. The next generation of stars formed from gas that was slightly enriched with these elements, allowing them to burn more efficiently and live longer. When these stars died, they added their own contribution to the growing inventory of cosmic metals. This process is beautifully illustrated in the different stellar populations we observe in galaxies today. The oldest stars, formed when the universe was just a few billion years old, have very low metallicities, sometimes less than 1% of the heavy element abundance we find in our Sun. These ancient stars are like archaeological artifacts, preserving in their atmospheres the chemical signature of the early universe. Younger stars, formed more recently from gas that had been processed through multiple stellar generations, show progressively higher metallicities. Our Sun, formed about 4.6 billion years ago, when the universe was already more than 2/3 of its current age, has a metallicity that's considered roughly average for stars in the Milky Way's disk. The heavy metal enrichment process wasn't uniform across the universe. Different types of stars contributed different elements to the cosmic inventory. Massive stars, which live fast and die young in supernova explosions, are the primary sources of oxygen, silicon, and iron. These elements are dispersed quickly after the star's death, enriching the surrounding interstellar medium within a few million years. Lower mass stars contribute to cosmic enrichment through a different pathway. Stars like our Sun evolve more slowly, and when they die, they shed their outer layers gently as planetary nebulae, contributing carbon, nitrogen, and other elements processed during their long lives. This process takes billions of years, meaning these elements were contributed to the cosmic inventory much later in cosmic history. The most dramatic contributors to heavy metal enrichment were the supernova explosions that marked the deaths of the most massive stars. These cosmic furnaces operated at temperatures of billions of degrees, hot enough to forge elements all the way up to iron and cobalt. Even heavier elements like gold, platinum, and uranium were created in the extreme conditions of these stellar explosions through rapid neutron capture processes. By the end of the Golden Age, the cosmic abundance pattern had been largely established. Hydrogen still dominated, making up about 70% of ordinary matter by mass, with helium accounting for most of the rest. But the heavy elements, though comprising less than 2% of the total mass, were crucial for everything that would follow. This chemical enrichment made possible the formation of dust grains in stellar atmospheres and supernova remnants. These tiny particles, composed of elements like carbon, silicon, and iron, would prove essential for efficient cooling of gas clouds, enabling the formation of smaller stars like our Sun. They would also provide the raw materials for rocky planets, asteroids, and comets. The universe had evolved from chemical simplicity to complexity, setting the stage for the next great chapter in cosmic evolution, the formation of planetary systems where complex chemistry could flourish. About 4.6 billion years ago, in an unremarkable spiral arm of an ordinary galaxy, something extraordinary was about to happen. A giant molecular clouder, vast stellar nursery containing enough material to build thousands of stars, began to collapse under its own gravity, setting in motion the events that would eventually lead to your existence. This wasn't just any molecular cloud. By cosmic standards, it was relatively late to the party, forming when the universe was already over 9 billion years old and had been through multiple generations of stellar birth, death, and chemical enrichment. The gas and dust in this cloud contained about 2% heavy elements carbon, oxygen, silicon, iron, and dozens of others forged in the cores of ancient stars and scattered by long-forgotten supernova explosions. That 2% made all the difference. While earlier generations of stars formed from nearly pure hydrogen and helium, our solar nebula was rich with the ingredients for complexity. Dust grains of silicon and carbon could form in the cold depths of the molecular cloud, providing surfaces where hydrogen atoms could combine into molecules and allowing the gas to cool efficiently. This cooling was cruciate, allowed smaller, more sun-like stars to form rather than only the massive giants of earlier epochs. The trigger for our solar system's formation may have been the shock wave from a nearby supernova explosion. Computer simulations suggest that such stellar explosions could compress nearby molecular clouds enough to initiate gravitational collapse. Ironically, the death of one massive star may have been the catalyst for the birth of our much smaller, longer-lived sun. As the cloud collapsed, it began to spin faster due to conservation of angular momentum, the same principle that causes figure skaters to spin faster when they pull their arms inward. This rotation prevented all the material from falling directly into the forming star at the center. Instead, it created a flattened, rotating disk of gas and dust surrounding the young sun. This protoplanetary disk was a chaotic, dynamic environment. The inner regions, heated by the young sun's radiation and gravitational energy release, reached temperatures of over 10 degrees Celsius, shot enough to vaporize most compounds, except the most refractory materials like iron and rock-forming silicates. Further out, beyond what we now call the frost line, temperatures were cool enough for water, ammonia, and other volatile compounds to condense into ice. This temperature gradient created fundamentally different conditions for planet formation in different regions of the solar system. Close to the sun, only rocky materials could condense, leading to the formation of small, dense terrestrial planets. Beyond the frost line, ice could form, providing much more raw material for planet building and enabling the formation of the massive gas giant planets. The process of planet formation began with dust grains sticking together through electrostatic forces and gentle collisions. These grain aggregates grew into pebbles, then boulders, then mountain-sized planetesimals, through a combination of continued accretion and gravitational attraction. It was like cosmic snowball fights, where every collision made the participants larger and more likely to win subsequent encounters. The formation of Jupiter, the solar system's largest planet, was a pivotal moment. Once Jupiter reached about 10 times Earth's mass, its gravity became strong enough to capture gas directly from the solar nebula, allowing it to balloon to its current size of over 300 Earth masses. Jupiter's formation may have taken less than 1 million years, incredibly fast by astronomical standards. Jupiter's presence had profound effects on the rest of the solar system. Its powerful gravity acted like a cosmic vacuum cleaner, capturing or ejecting many small bodies that might otherwise have bombarded the inner planets. But it also prevented a planet from forming in what is now the asteroid belt, leaving behind only scattered remnants of what might have been another world. The terrestrial planets formed through a more violent process called accretion. Countless planetesimals crashed into growing planetary embryos over tens of millions of years. Each impact released enormous amounts of energy, keeping the forming planets molten. Earth grew through this process, experiencing countless catastrophic collisions that gradually built up its mass. The most dramatic of these collisions occurred relatively late in Earth's formation, when a Mars-sized object called Theia struck our planet at an oblique angle. This impact was so energetic that it vaporized both objects, creating a debris disk around Earth, from which the Moon would eventually coalesce. The angular momentum from this collision is why Earth rotates once every 24 hours, and why the Moon orbits our planet. The early solar system was a much more chaotic place than today. The late heavy bombardment, which occurred about 4.1 billion years ago, saw a renewed period of intense impacts as gravitational perturbations sent swarms of asteroids and comets careening through the inner solar system. Evidence of this bombardment is still visible today in the heavily cratered surfaces of the Moon and Mercury. But this apparent chaos was actually fine-tuning the solar system for habitability. The bombardment brought water and organic compounds from the outer solar system to Earth. Comets, essentially dirty snowballs from the frigid outer reaches of the solar system, delivered the ingredients for oceans and potentially even the precursor molecules for life. By about 4 billion years ago, the major construction phase of solar system formation was complete. The Sun had settled into stable nuclear burning, the planets had cleared their orbits of most remaining debris, and Earth had cooled enough for liquid water to exist on its surface. The stage was set for the next great chapter in cosmic evolution, the emergence of life itself. Our solar system's formation represents just one example of a process that was occurring throughout the galaxy during this epoch. The heavy element enrichment of the previous billions of years had made planetary systems like ours possible for the first time in cosmic history. We are the products of stellar recycling on a cosmic scale, built from the ashes of stars that died billions of years before our sun was born. The Earth that emerged from the chaos of solar system formation 4.5 billion years ago would have been completely unrecognizable to any modern observer. This was not the blue marble we know today, with its white clouds, green continents, and sparkling oceans. This was a hellish world of molten rock, toxic atmospheres, and constant bombardment from a planet that seemed utterly hostile to life, yet was secretly preparing to become its greatest sanctuary. Young Earth was still glowing from the heat of formation. The countless impacts that built our planet from countless smaller bodies had released enormous amounts of kinetic energy, keeping the entire world molten. The surface was an ocean of magma, continuously churned by convection currents that brought hot material up from below, while sending cooled rock back down into the depths. Temperatures at the surface exceeded 200 degrees Celsius, shot enough to melt copper. The atmosphere of this primordial Earth was nothing like the life-sustaining mixture we breathe today. There was no oxygen that would come much later, as a byproduct of photosynthetic life. Instead, the atmosphere was dominated by hydrogen and helium captured from the solar nebula, along with gases released by volcanic outgassing, water vapor, carbon dioxide, nitrogen, methane, ammonia, and hydrogen sulfide. It was a poisonous cocktail that would be instantly lethal to any complex life form. But this hostile atmosphere was short-lived in geological terms. The intense solar wind from the young sun, which was much more active and violent than today, gradually stripped away the primordial atmosphere. Additionally, the lack of a magnetic field Earth's core was still cooling, and solidifying meant that our planet offered no protection against this solar assault. Within a few 100 million years, most of the original atmosphere had been lost to space. The bombardment from space continued relentlessly during Earth's first billion years. Asteroids and comets, leftover debris from solar system formation, pelted the surface in a cosmic shooting gallery. Some of these impacts were truly catastrophic, large enough to vaporize any oceans that might have formed and potentially sterilize the entire planet. The largest impacts created craters hundreds of kilometers across, and threw so much debris into space that some of it may have reached the moon. Yet paradoxically, this bombardment was also delivering the ingredients that would eventually make life possible. Comets from the outer solar system brought water, ice, and organic compounds to Earth's surface. Asteroids delivered metals and other heavy elements. Each impact was simultaneously destructive and creative, adding to Earth's inventory of materials while reshaping the planet's surface. The formation of Earth's moon through the giant Theia impact had profound consequences for our planet's evolution. The moon's gravitational pull created tides that were much more extreme than today. The moon was initially much closer to Earth, and has been gradually spiraling outward ever since. These powerful tides may have helped mix the early oceans, distributing heat and chemicals that would be important for the eventual emergence of life. The moon also stabilized Earth's axial tilt, preventing our planet from tumbling chaotically and ensuring relatively stable climatic conditions over geological time. Without the moon, Earth's axis might wobble dramatically, causing extreme climate variations that could make the evolution of complex life much more difficult. As Earth continued to cool, water vapor in the atmosphere began to condense. The first rains fell on a world where surface temperatures were still above the boiling point of water, causing the raindrops to turn back into steam before reaching the ground. But gradually, as heat continued to radiate away into space, surface temperatures dropped below 100 degrees Celsius, and liquid water could finally exist on the surface. The formation of the first oceans marked a crucial transition in Earth's evolution. Water is not just essential for life as we know it, it's also a powerful geological agent. The early oceans began weathering the rock surfaces, dissolving minerals and creating the first sediments. They also helped regulate Earth's temperature through the greenhouse effect of water vapor and the heat capacity of liquid water. Earth's internal structure was also taking shape during this violent youth. Denser materials like iron sank toward the center through a process called differentiation, while lighter materials rose toward the surface. This process generated enormous amounts of heat and established the layered structure we see today: an iron-nickel core, a rocky mantle, and a thin crust. The formation of Earth's magnetic field began as the iron core started to solidify and convect. This magnetic field would prove crucial for protecting the atmosphere and any future life from harmful solar and cosmic radiation. Without it, Earth might have suffered the same fate as Mars, gradually losing its atmosphere to space. By about 4 billion years ago, Earth had transformed from a molten hellscape into a world with solid continents, liquid oceans, and a stable atmosphere. The stage was finally set for the next great chapter in our planet's story, the emergence of the first living cells. Somewhere in the ancient oceans of a young Earth, roughly 3.8 billion years ago, chemistry crossed a threshold that had never been crossed before in the known universe. Complex molecules began to organize themselves, capture energy, make copies of themselves, and evolve. Life had emerged from the realm of pure chemistry, marking the beginning of biology and setting Earth on a path that would eventually lead to conscious beings capable of contemplating their own origins. The emergence of life represents perhaps the most profound mystery in all of science. How do you bridge the gap between complex chemistry and simple biology? How do you get from molecules that follow the laws of physics and chemistry to systems that can grow, reproduce, and evolve? Scientists call this the origin of life problem, and despite decades of research, we still don't have a complete answer. What we do know is that early Earth provided a natural laboratory perfectly suited for chemical experimentation. The planet's surface was a dynamic environment with volcanic activity, lightning storms, hydrothermal vents, and tidal pools, all sources of energy that could drive complex chemical reactions. The atmosphere lacked oxygen, which would have been destructive to complex organic molecules, but contained methane, ammonia, and other compounds that could serve as building blocks for larger molecules. The raw materials for life were abundant. Carbon, with its unique ability to form 4 chemical bonds, provided the backbone for complex organic molecules. Water served as the universal solvent, allowing chemical reactions to occur and providing a medium for molecular transport. Nitrogen and phosphorus were available to build the information-carrying molecules that would become DNA and RNA. One of the leading theories for life's origin involves RNA, a molecule that can both store genetic information like DNA and catalyze chemical reactions like proteins. This RNA world hypothesis suggests that RNA molecules were the first self-replicating systems, able to make copies of themselves while also evolving through random mutations. Over time, these RNA systems became more sophisticated, eventually giving rise to the DNA protein machinery that dominates life today. The first living cells were incredibly simple by modern standard single-celled organisms called prokaryotes, lacking the complex internal structures found in modern cells. These early organisms were anaerobic, meaning they lived without oxygen, which was essentially absent from Earth's early atmosphere. Instead, they derived energy from chemical reactions involving hydrogen, methane, sulfur compounds, and other substances abundant in the early environment. Some of the earliest evidence for life comes from structures called stromatolite-layered rock formations, created by ancient bacterial communities. These fossils, found in rocks as old as 3.5 billion years, preserve the remains of microbial mats that grew in shallow seas. The bacteria in these communities captured and precipitated minerals from seawater, creating the distinctive layered structures we can still observe today. But perhaps the most remarkable thing about these early life forms was their diversity. Evolution began experimenting with different approaches to the problem of survival almost immediately. Some early organisms were photosynthetic, using sunlight to power their metabolism. Others were chemosynthetic, deriving energy from chemical reactions involving rocks and minerals. Still others were heterotrophic, consuming organic molecules created by other organisms. The early biosphere was dominated by these microbial communities for over 1 billion years. While it might seem like a time of biological stagnation compared to the rapid changes that would come later, this was actually a period of intense innovation at the cellular level. Early life forms evolved the fundamental biochemical pathways that still power all life today: photosynthesis, respiration, DNA replication, protein synthesis, and cellular reproduction. Some of these early organisms began experimenting with a new form of photosynthesis that would have profound consequences for Earth's future. Unlike earlier forms of photosynthesis that used hydrogen sulfide or other compounds, This new process used water as a source of electrons. The byproduct of this reaction was oxygen, initially just a waste product, but one that would eventually transform our planet's atmosphere and enable the evolution of complex life. The first living cells also established the basic principles of evolution that continue to operate today. Random mutations in their genetic material created variation within populations, while natural selection favored those variants that were better adapted to their environments. Over millions of generations, this process led to increasing complexity and diversity. These early organisms faced challenges that would be familiar to life today: finding resources, avoiding toxins, reproducing successfully, and competing with other organisms for limited space and nutrients. The solutions they evolved: metabolic pathways, cellular membranes, genetic codes, and repair mechanisms provided the foundation for all subsequent life on Earth. By 3 billion years ago, microbial life had spread throughout Earth's oceans and was beginning to have a measurable impact on the planet's chemistry and atmosphere. The stage was set for the next great transition in Earth's history, the oxygen revolution that would pave the way for complex life. About 2.4 billion years ago, Earth experienced what scientists call the Great Oxidation Event, a planetary transformation so dramatic that it represents one of the most significant environmental changes in our planet's history. For the first time, oxygen began to accumulate in significant quantities in Earth's atmosphere, setting the stage for the evolution of complex life, while simultaneously causing one of the greatest extinction events the planet has ever seen. The architects of this revolution were tiny cyanobacteria, single-celled organisms that had evolved a new and powerful form of photosynthesis. Unlike earlier photosynthetic organisms that used hydrogen sulfide or organic compounds as electron donors, cyanobacteria learned to split water molecules, using the hydrogen to build organic compounds and releasing oxygen as a waste product. This innovation was extraordinarily successful from the cyanobacteria's perspective. Water was abundant, and sunlight provided an essentially unlimited energy source. Cyanobacterial communities began to flourish in shallow seas around the globe, forming vast microbial mats that dominated many marine environments. For the first time in Earth's history, life was producing oxygen faster than it could be consumed by chemical reactions with rocks and dissolved metals. But oxygen was toxic to most existing life forms. The early biosphere had evolved in an oxygen-free environment, and most organisms lacked the biochemical machinery to deal with this reactive gas. Oxygen is chemically aggressive. It readily forms harmful compounds called free radicals that can damage cellular structures and DNA. For billions of anaerobic organisms, the rising oxygen levels represented an existential threat. The result was a mass extinction that may have wiped out most of Earth's existing biodiversity. Scientists sometimes call this the oxygen holocaust, or oxygen catastrophe, the first major extinction event in Earth's history, caused not by an asteroid impact or volcanic eruption, but by life itself fundamentally altering the planet's chemistry. However, the crisis also created opportunities. Some organisms evolved biochemical defenses against oxygen, developing enzymes like catalase and superoxide dismutase that could neutralize dangerous oxygen compounds. Even more importantly, some organisms learned to use oxygen for a new type of metabolism called aerobic respiration. Aerobic respiration is incredibly efficient compared to the anaerobic processes that dominated early life. While anaerobic organisms might extract 2 molecules of ATP, the cellular energy currency, from a glucose molecule, aerobic organisms can extract 36 molecules of ATP from the same starting material. This 18-fold increase in metabolic efficiency provided the energy foundation that would eventually support the evolution of complex multicellular life. The accumulation of atmospheric oxygen also had profound effects on Earth's surface chemistry. Iron dissolved in the oceans reacted with oxygen to form iron oxides that precipitated out as sediments, creating the distinctive banded iron formations that we still find in rocks from this period. These geological formations provide some of our best evidence for the timing and pace of the Great Oxidation Event. Oxygen in the atmosphere also led to the formation of the ozone layer. When oxygen molecules are split by ultraviolet radiation high in the atmosphere, they can recombine to form ozone, which absorbs harmful UV radiation. This ozone shield made it possible for life to eventually colonize land surfaces without being destroyed by solar radiation. The oxygen revolution wasn't a sudden event, but rather a gradual process that took hundreds of millions of years to complete. Atmospheric oxygen levels rose slowly at first, then more rapidly as oxygen-producing organisms spread and diversified. The transition also wasn't monotonic. There were periods when oxygen levels rose and fell as the Earth system found its new equilibrium. By about 1.8 billion years ago, atmospheric oxygen had reached levels that could support the evolution of more complex cellular organisms. The stage was set for the next great innovation in the history of life, the evolution of cells with nuclei and other internal structures that would make complex multicellular life possible. Around 2 billion years ago, in the oxygen-enriched oceans of Earth, one of the most consequential events in the history of life occurred. It wasn't marked by dramatic explosions or sudden changes, but by a quiet cellular merger that would revolutionize the possibilities for biological complexity. A large cell engulfed a smaller one, and instead of digesting it, the two began living together in what would become one of evolution's most successful partnerships. This event marked the origin of eukaryotic cells with nuclei and other internal structures called organelles. The name comes from the Greek words for true kernel, referring to the membrane-bound nucleus that houses genetic material. This might seem like a minor architectural change, but it was actually a revolutionary leap that made possible everything from mushrooms to maple trees, from jellyfish to humans. The smaller cell that was engulfed was likely a bacterium capable of aerobic respiration, of those organisms that had learned to use oxygen efficiently for energy production. Instead of being destroyed, it became a permanent resident inside its host, eventually evolving into what we now call mitochondria. These cellular powerhouses use oxygen to generate ATP with remarkable efficiency, providing the energy foundation that makes complex life possible. This process, called endosymbiosis, happened multiple times during early eukaryotic evolution. Another crucial merger involved cyanobacteria, which became chloroplasts in plant cells. These organelles retain their ability to perform photosynthesis, allowing their host cells to harness sunlight directly. Every green plant you see today is actually a community of formerly independent organisms that learned to work together so successfully that they became inseparable. The evidence for endosymbiosis is written in the genetic code itself. Mitochondria and chloroplasts have their own DNA, separate from the main cellular genome, and this DNA shows clear evolutionary relationships to free-living bacteria. Even more convincing, these organelles reproduce by dividing in two, just like bacteria, rather than being assembled from scratch by the host cell. The evolution of eukaryotic cells represented a quantum leap in biological complexity. With mitochondria providing abundant energy, eukaryotic cells could grow much larger than their prokaryotic ancestors and support much more sophisticated cellular machinery. The nucleus provided a secure location for genetic material, while other membrane-bound compartments allowed different chemical processes to be isolated and optimized. But perhaps most importantly, eukaryotic cells invented sex. Well, not sex as we typically think of it, but rather sexual reproduction, the process by which two organisms contribute genetic material to create offspring that are genetically distinct from either parent. This was a profound innovation because it dramatically accelerated the pace of evolution. In asexual reproduction, offspring are essentially clones of their parents, and genetic diversity can only increase through random mutations. Sexual reproduction, by contrast, shuffles genetic material from two parents, creating countless new combinations of genes in each generation. This genetic recombination allows beneficial mutations from different lineages to be combined while helping to eliminate harmful mutations from populations. The evolution of sexual reproduction also required the development of specialized reproductive cells called gamete tessels that contain only half the normal genetic material. When two gametes merge during fertilization, they restore the full genetic complement while creating a unique new individual. This process, called meiosis, is one of the most complex cellular processes in biology, involving precise chromosome pairing and separation that must occur without errors. Sexual reproduction initially evolved in single-celled eukaryotes, but it set the stage for an even more remarkable innovation: multicellularity. Individual cells began to stick together after reproduction, forming colonies that could eventually evolve specialized cell types. Some cells might focus on reproduction, while others handled feeding, defense, or movement. This division of labor allowed multicellular organisms to become much more sophisticated than any single cell could be alone. The transition to multicellularity happened independently many times in different lineages in plants, animals, fungi, and various protist groups. Each evolutionary experiment with multicellularity explored different solutions to the challenges of coordinating multiple cells, leading to the incredible diversity of complex life we see today. Early multicellular organisms were simple affairs collections of similar cells that cooperated, but hadn't yet evolved the sophisticated tissues and organs of modern plants and animals. But they represented a crucial proof of concept. Individual cells could sacrifice their independence for the benefits of cooperation, and the resulting organisms could be more successful than their single-celled ancestors. The emergence of complex life also required innovations in cellular communication. Cells needed ways to send signals to each other, coordinate their activities, and respond collectively to environmental changes. The evolution of cell surface receptors, chemical messengers, and signaling pathways provided the communication networks that made multicellular life possible. These early experiments in complexity were taking place in a world that was still dominated by microbial life. For most of Earth's first 3 billion years, bacteria and archaea were the only life forms on the planet. The evolution of eukaryotic cells represented the beginning of a new chapter in Earth's story, but it would take another billion years for complex multicellular organisms to become prominent features of Earth's biosphere. The oxygen-rich atmosphere that made complex life possible also enabled new forms of metabolism and biochemistry. Organisms could now use oxygen not just for energy production, but as a raw material for synthesizing complex molecules. This oxygen chemistry would prove essential for building the structural proteins, defensive compounds, and signaling molecules that complex life requires. By about 1 billion years ago, the stage was set for the next great explosion of biological innovation. Complex cells had evolved the basic machinery for multicellular life. Sexual reproduction was shuffling genes and accelerating evolution, and atmospheric oxygen levels were approaching modern levels. Earth was ready for the emergence of large, complex organisms that would eventually colonize every environment on the planet. About 540 million years ago, Earth experienced what paleontologists call the Cambrian Explosione, relatively sudden burst of evolutionary innovation that filled the oceans with an unprecedented diversity of complex animals. In the geological blink of an eye, perhaps 15 to 20 million years, most of the major animal body plans that exist today appeared in the fossil record, along with many bizarre experimental forms that have no modern equivalents. This wasn't just an increase in the number of species, it was a fundamental revolution in the complexity and diversity of life itself. For over 3 billion years, life had consisted primarily of single-celled organisms and simple multicellular forms. Suddenly, the oceans were teeming with creatures that had eyes, shells, spines, jointed legs, and sophisticated predatory behaviors. It was as if nature had been sketching simple drawings for billions of years, and then suddenly began creating three-dimensional sculptures. The trigger for this explosion remains one of paleontology's greatest mysteries, but several factors likely contributed to this remarkable burst of innovation. Rising atmospheric oxygen levels had finally reached concentrations that could support the metabolism of large, active animals. The evolution of predation created evolutionary arms races that drove rapid innovation in both offensive and defensive capabilities. And the genetic toolkit for building complex body plans, including regulatory genes that controlled development, had finally evolved to the point where major evolutionary experiments became possible. One of the most remarkable aspects of the Cambrian explosion was the sudden appearance of complex eyes. Vision is such a powerful sense that once it evolved, it fundamentally changed the nature of life on Earth. Predators could hunt more efficiently, prey animals needed better escape mechanisms, and the entire ecosystem became more dynamic and interactive. The trilobites, one of the most successful Cambrian groups, evolved compound eyes with up to 15.0 individual lenses, a level of optical sophistication that wouldn't be matched by human technology until the development of modern cameras. The Burgess Shale in Canada preserves one of our best windows into this ancient world, capturing creatures so bizarre that paleontologists initially struggled to classify them. Opabinia had 5 eyes and a grasping proboscis tipped with a claw. Hallucigenia walked on spines and had a back covered with defensive spikes. Wiwaxia looked like a medieval knight's helmet covered in scales and spines. These weren't just variations on familiar themes. They represented entirely different approaches to the problem of being a complex animal. Many of these experimental body plans were evolutionary dead-ends lineages that flourished briefly during the Cambrian but left no descendants. This suggests that the early Cambrian was a time of exceptional evolutionary experimentation, when many different solutions to the challenges of complex life were being tested simultaneously. Most failed, but the survivors became the ancestors of all modern animals. The evolution of hard shells and skeletons was another crucial innovation of this period. These structures served multiple purposes: protection from predators, structural support for larger body sizes, and attachment points for muscles that enabled more sophisticated locomotion. The sudden appearance of hard parts in the fossil record also explains why the Cambrian explosion seems so abrupt. Soft-bodied organisms rarely fossilize, so the earlier evolution of complex life is largely invisible to us. Predation became a major evolutionary force for the first time during the Cambrian. Creatures like Anomalocaris, with its flexible feeding arms and circular mouth, were the first large predators in Earth's history. The presence of active hunters created selection pressure for prey species to evolve better defenses, leading to an evolutionary arms race that drove rapid morphological innovation. The Cambrian seas were also the birthplace of many of the animal phyla we recognize today. Arthropods, including trilobites, ancestors of modern insects and crustaceans; mollusks, early relatives of snails, clams, and squid; echinoderms, ancestors of starfish and sea urchins; and early chordates, our own evolutionary lineage, all made their first appearances during this period. Perhaps most significantly for our own story, the Cambrians saw the evolution of the first animals with primitive nervous systems and the beginnings of centralized information processing. While these early neural networks were simple compared to modern brains, they represented the first steps toward the complex nervous systems that would eventually give rise to consciousness and intelligence. The end of the Cambrian explosion, around 520 million years ago, marked a transition from evolutionary experimentation to evolutionary refinement. The basic body plans had been established, and subsequent evolution would focus on variations and improvements within these fundamental frameworks, rather than inventing entirely new approaches to complex life. The Cambrian explosion demonstrates evolution's incredible creativity when the right conditions converge. It shows us that major evolutionary innovations can occur relatively rapidly when environmental conditions change and new ecological opportunities become available. Most importantly for our cosmic story, it marked the beginning of complex ecosystems and the evolutionary lineages that would eventually lead to intelligence and consciousness. For nearly 4 billion years, life on Earth was confined to water. The oceans, lakes, and rivers provided everything living organisms needed: a stable temperature environment, protection from harmful radiation, dissolved nutrients, and the buoyant support that made movement possible without complex structural support systems. But around 470 million years ago, life began one of its most ambitious experiments: the colonization of land. This transition represented an enormous challenge. Land was a harsh, alien environment compared to the gentle embrace of water. There was no protection from ultraviolet radiation. Temperatures fluctuated wildly between day and night, and there was no water to provide buoyancy or dissolved nutrients. Any organism venturing onto land would need to solve problems that had never existed before: how to support body weight against gravity, how to prevent water loss, how to breathe air instead of extracting dissolved gases from water, and how to reproduce without aquatic environments. The first pioneers were likely simple plants, probably similar to modern mosses and liverworts. These early colonists stayed close to water, growing in moist environments where they could still rely on water for reproduction and support. They were small, lacking the sophisticated vascular systems that would later allow plants to grow tall and transport water and nutrients over long distances. But even these humble beginnings had profound consequences. For the first time in Earth's history, photosynthesis began occurring on land, altering atmospheric chemistry and local climate patterns. Plant roots began breaking down rocks, creating the first soils, and accelerating the weathering processes that cycle elements between the atmosphere, biosphere, and geosphere. The evolution of vascular systems in plants' networks of tubes that could transport water and nutrients was a crucial innovation that opened up vast new territories for colonization. These vascular plants could grow away from water sources, extending roots deep into the ground to find moisture and nutrients, while raising their photosynthetic organs high into the air to capture sunlight. Early forests began to appear around 385 million years ago, dominated by primitive trees like Archaeopteris. These weren't the flowering trees we know today, but they represented a revolutionary new form of life that could build complex three-dimensional structures on land. Forests created new environment-shaded understories, complex soil systems, and aerial habitats that had never existed before. Animals followed plants onto land, but they faced even greater challenges. The first terrestrial animals were likely arthropod creatures, with jointed legs and external skeletons that could provide structural support out of water. Millipedes and primitive arachnids were among the early colonists, feeding on decomposing plant material and each other. The evolution of lungs represented a crucial breakthrough for animal life on land. Fish had gills optimized for extracting dissolved oxygen from water, but air breathing required entirely different anatomical structures. Some early fish evolved primitive lungs as supplementary breathing organs, allowing them to survive in shallow, oxygen-poor waters. These lung-equipped fish became the ancestors of all land vertebrates. The development of waterproof skin and efficient kidneys was essential for preventing fatal water loss. Early terrestrial animals also needed new reproductive strategies, since their aquatic ancestors relied on water for fertilization and early development. The evolution of internal fertilization and protective eggshells allowed reproduction to occur in dry environments. One of the most significant innovations was the amniotic egg, with internal membranes that create a protected aquatic environment for the developing embryo. This innovation, which appeared around 340 million years ago, freed animals from the need to return to water for reproduction and enabled the rapid diversification of reptiles, birds, and mammals. The colonization of land also drove the evolution of more sophisticated nervous systems and sensory organs. Navigation on land required different skills than in water, and the three-dimensional complexity of forest environments provided new opportunities for complex behaviors. Enhanced vision, hearing, and chemical detection became increasingly important for survival. By 300 million years ago, complex terrestrial ecosystems had evolved, with multiple trophic levels including plants, herbivores, carnivores, and decomposers. The stage was set for even more sophisticated forms of life to evolve, including the lineages that would eventually give rise to intelligence and consciousness. The emergence of consciousness represents perhaps the most profound mystery in the entire 13.8 billion year history of the universe. How does the collection of atoms forged in ancient stellar cores become aware of itself? How does matter organized by the laws of physics develop the capacity for subjective experience, self-reflection, and the contemplation of its own cosmic origins? The story of consciousness begins with the evolution of nervous systems networks of specialized cells that could process information, coordinate responses, and store memories. The first primitive neural networks appeared during the Cambrian explosion, simple clusters of nerve cells that could detect stimuli and coordinate basic behaviors. These early brains were nothing like the complex organs we know today, but they represented the first steps towards centralized information processing. For hundreds of millions of years, nervous systems grew more sophisticated through evolutionary pressures that favored better sensory processing, more coordinated movement, and improved behavioral flexibility. Predators needed to track and capture prey efficiently, while prey animals required quick reflexes and escape strategies. Social animals needed to recognize individuals, remember relationships, and coordinate group behaviors. The vertebrate brain evolved through a series of expansions and reorganizations. Fish developed the basic brain architecture that we still carry today: a hindbrain for basic life functions, a midbrain for sensory processing and reflexes, and a forebrain that would eventually become the seat of higher cognitive functions, As vertebrates colonized land and faced new environmental challenges, their brains became increasingly complex and capable. Mammals, which evolved around 200 million years ago, developed several neural innovations that would prove crucial for the eventual emergence of consciousness. They evolved a more sophisticated cerebral cortex, the folded outer layer of the brain where complex information processing occurs. They also developed advanced systems for emotional regulation, social bonding, and parental care that required more nuanced behavioral control. The evolution of warm-bloodedness in mammals and birds created the metabolic foundation for energy-expensive brains. Neural tissue consumes enormous amounts of energy. The human brain, representing just 2% of body weight, uses about 20% of our total energy expenditure. Only organisms with high-efficiency metabolisms could afford to build and operate large, complex brains. Primates, which evolved around 55 million years ago, developed several characteristics that would prove important for advanced cognition. Their forward-facing eyes provided stereoscopic vision, crucial for depth perception, while moving through three-dimensional forest environments. Their grasping hands with opposable thumbs allowed sophisticated tool use and manipulation of objects. Perhaps most importantly, many primate species evolved complex social structures that created selection pressure for advanced cognitive abilities. The great apes, our closest relatives, demonstrate many of the cognitive abilities we associate with consciousness. They show self-awareness, as demonstrated by their ability to recognize themselves in mirrors. They use tools, solve complex problems, and display emotional responses that seem remarkably similar to our own. They can learn symbolic communication systems and demonstrate what appears to be theory of mind, the understanding that other individuals have their own thoughts and perspectives. The human lineage diverged from our closest living relatives around 7 million years ago, and several key developments during human evolution may have been crucial for the emergence of full consciousness as we experience it. The evolution of bipedalism freed our hands for tool use and manipulation, while changing the structure of our pelvis in ways that would later affect brain development. About 2.8 million years ago, our ancestors began making stone tools, marking the beginning of a feedback loop between technology and brain evolution. Tool use required planning, problem-solving, and fine motor control, creating selection pressure for enhanced cognitive abilities. Improved tools enabled new behaviors and survival strategies, which in turn selected for even more advanced cognition. The control of fire, beginning perhaps 800 years ago, had profound implications for human development. Cooking food made nutrients more bioavailable and reduced the energy required for digestion, potentially freeing up energy for brain growth. Fire also extended the active day and created new social contexts where information sharing and cultural transmission could occur. Language represents perhaps the most crucial innovation in the development of human consciousness. While other animals communicate, human language is uniquely flexible, creative, and symbolic. Language allows us to share not just information about the immediate environment, but abstract concepts, memories of the past, and plans for the future. It enables cumulative cultural evolution, where knowledge can be preserved and built upon across generations. The archaeological record suggests that fully modern human behavior, including art, music, complex tool technologies, and symbolic thought emerged around 100 years ago. Cave paintings, carved figurines, and musical instruments from this period demonstrate capacities for abstract thought, aesthetic appreciation, and symbolic representation that are hallmarks of consciousness as we experience it. But consciousness isn't just a human phenomenon. Evidence suggests that many animals possess varying degrees of conscious experience. Elephants appear to mourn their dead and show self-awareness. Dolphins recognize themselves in mirrors and demonstrate cultural transmission of behaviors. Even some birds, despite having very different brain structures than mammals, display remarkable cognitive abilities, including tool use, problem-solving, and apparent self-awareness. The emergence of consciousness in humans eventually led to the development of science, the systematic investigation of natural phenomena that has allowed us to understand our place in the cosmic story. Through science, conscious beings have been able to trace their origins back to the Big Bang, understand the nuclear processes that forged the elements in their bodies, and contemplate the future evolution of the universe itself. This represents an extraordinary development in cosmic evolution. For the first time in 13.8 billion years, the universe has produced structures capable of understanding themselves and their origins. Through human consciousness, the cosmos has developed the capacity for self-reflection and self-awareness on a cosmic scale. The rise of consciousness marks a new phase in the universe's evolution, one where information processing, rather than just energy and matter, becomes a driving force in cosmic development. Conscious beings can now deliberately shape their environment, preserve and transmit knowledge across time, and even begin to influence the future evolution of life itself. For most of human history, we lived in a universe that seemed small, Earth-centered, and comprehensible. The stars were points of light on a celestial sphere that rotated around us each night. The sun and moon were divine objects that marked the passage of days and seasons. Our world was the center of creation, and we were the purpose for which everything else existed. But beginning about 400 years ago, humans began systematically challenging this comfortable cosmic perspective. What started as curiosity about planetary motions gradually revealed that we inhabit a universe far stranger, larger, and more magnificent than anyone had ever imagined. The journey from geocentric mythology to cosmic awareness represents one of the greatest intellectual achievements in human history. Galileo Galilei was among the first to point a telescope at the night sky in 1609, and what he saw shattered the ancient worldview. The moon wasn't a perfect celestial sphere, but a world with mountains and craters. Jupiter had its own moons, proving that Earth wasn't the center of all celestial motion. The Milky Way, which appeared as a faint band of light to the naked eye, resolved into countless individual stars. The universe was suddenly much larger and more complex than anyone had imagined. The Copernican revolution displaced Earth from the center of the universe, but it took centuries for humans to fully grasp the implications. In the 1920s, Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to make observations that would revolutionize our understanding of cosmic scale. What astronomers had long called spiral nebulae were actually other galaxies' entire star systems so distant that their light had traveled for millions of years to reach us. Even more shocking was Hubble's discovery that these distant galaxies were moving away from us, and that the farther away they were, the faster they were receding. This observation led to the realization that the universe itself was expanding, not expanding into something, but rather that space itself was growing, carrying galaxies along with it like raisins in rising bread dough. The implications were staggering. If the universe was expanding now, it must have been smaller in the past. Working backward through time, astronomers realized that everything we can observe must once have been compressed into an incredibly hot, dense state. The Big Bang Theory was born from astronomical observations, providing the first scientific account of cosmic origins. Throughout the 20th century, each new astronomical discovery seemed to make the universe larger, stranger, and more wonderful. Radio astronomy revealed quasar objects so luminous they could be seen across billions of light-years. X-ray astronomy discovered black holes, neutron stars, and violent processes occurring in environments where the normal laws of physics are pushed to their limits. Space-based telescopes like Hubble opened new windows on the cosmos, revealing the births and deaths of stars, the formation of planetary systems, and the deep structure of space-time itself. But perhaps the most humbling discovery was the realization that everything we can see, every star, every galaxy, every planet represents less than 5% of the universe. The rest is composed of mysterious dark matter and dark energy that we can detect only through their gravitational effects. We are not just physically small compared to the cosmos. We are made of a minority component in a universe dominated by substances we don't understand. The search for life beyond Earth has been one of the most compelling aspects of humanity's cosmic awakening. The discovery of exoplanets, planets orbiting other starshars, revealed that planetary systems are common throughout the galaxy. We now know of thousands of exoplanets, including many in the habitable zones where liquid water might exist on their surfaces. This expanding cosmic perspective has profound implications for how we understand ourselves. We are not the center of the universe, either spatially or biologically. Earth is one planet among billions in our galaxy, which is itself one galaxy among hundreds of billions in the observable universe. Life on Earth represents a single example of biological evolution, and there may be countless other forms of life evolving in conditions we can barely imagine. Yet this apparent cosmic insignificance paradoxically reveals human significance in a deeper way. We are the product of 13.8 billion years of cosmic evolution. The carbon in our bodies was forged in the cores of dying stars. The oxygen we breathe was created by ancient cyanobacteria that transformed Earth's atmosphere. The complex chemistry that makes our thoughts possible required billions of years of stellar nucleosynthesis to create the heavy elements essential for life. Modern cosmology has revealed that conscious beings like ourselves represent something genuinely new and remarkable in cosmic history. For the first time since the Big Bang, the universe has produced structures capable of understanding their own origins and contemplating their cosmic context. Through science, humans have become the universe's way of understanding itself. This cosmic perspective doesn't diminish human importance. It reveals our true significance as conscious beings capable of comprehending the magnificent story of which we are a part. In 1998, two teams of astronomers studying distant supernovae made a discovery so unexpected that it fundamentally changed our understanding of the universe's fate. They were trying to measure how much the expansion of the universe was slowing down due to the gravitational attraction of all the matter it contains. Instead, they found something that challenged everything cosmologists thought they knew. The expansion of the universe is accelerating. This discovery was so surprising that the astronomers themselves initially doubted their results. For decades, cosmologists had assumed that gravity would gradually slow the universe's expansion, perhaps even eventually causing it to collapse back in on itself in a big crunch. The question wasn't whether expansion was slowing down, but by how much. The idea that expansion might be speeding up violated all conventional wisdom about how gravity should work on cosmic scales. The evidence came from observations of type Ia supernova stellar explosions that serve as standard candles, because they all reach approximately the same peak brightness. By comparing how bright these supernovae appear from Earth with how bright they should be at their actual distances, astronomers can measure how far away they are and how fast they were receding when the light was emitted billions of years ago. What the supernova teams found was that distant supernovae were dimmer than expected, meaning they were farther away than calculations, based on their redshift, would predict. This could only happen if the universe's expansion had accelerated since the light left those distant galaxies. Something was acting like cosmic anti-gravity, pushing space itself apart at an ever-increasing rate. This mysterious force-driving acceleration has been dubbed dark energy, though the name reflects our ignorance more than any understanding of its nature. Dark energy appears to make up about 70% of the universe's total energy content, making it the dominant component of reality as we know it. Yet we have no idea what it is, where it comes from, or why it exists. The leading theoretical candidate for dark energy is the cosmological constanta property of space itself that Einstein first proposed and later called his greatest blunder. According to this idea, empty space contains a uniform energy density that doesn't dilute as the universe expands. As the universe grows larger, there's more space, and therefore more dark energy, creating an accelerating feedback loop. But there are profound problems with this explanation. When physicists try to calculate what the cosmological constant should be based on quantum mechanical principles, they get an answer that's wrong by a factor of 10, 120, arguably the worst prediction in the history of science. Either our understanding of quantum mechanics is fundamentally flawed, or dark energy has some other, completely unknown origin. Alternative theories propose that dark energy might be a dynamic field, similar to the inflaton field that drove cosmic inflation in the first moments after the Big Bang. This quintessence field would evolve over time, potentially explaining why dark energy seems to have become important only in the recent cosmic past. Other theories suggest that our understanding of gravity itself might need modification on cosmic scales. The discovery of cosmic acceleration has profound implications for the universe's ultimate fate. Instead of eventually collapsing or reaching a stable size, our universe appears destined for eternal expansion at an ever-increasing rate. This means that the cosmic structures we see today, galaxy clusters, individual galaxies, even gravitationally bound systems like our solar system, represent temporary islands of order in a cosmos that will become increasingly empty and cold. As acceleration continues, distant galaxies will eventually recede so fast that their light can never reach us. The observable universe will shrink, and future astronomers will lose access to the cosmic microwave background and other distant phenomena that have been crucial for understanding cosmic history. In a sense, we are living during a special epoch when the universe is old enough to have developed complexity but young enough that we can still observe the evidence for cosmic evolution. The implications extend even further into the future. If dark energy remains constant, the acceleration will eventually become so extreme that it tears apart all gravitationally bound structures. First, galaxy clusters will dissolve as their member galaxies are carried apart by expanding space. Then individual galaxies will be disrupted, followed by star systems, planets, and eventually even atoms themselves, in what cosmologists call the Big Rip. However, this extreme scenario depends on the precise nature of dark energy, which remains completely mysterious. If dark energy is indeed a cosmological constant, the universe will expand exponentially, but won't tear apart bound structures. If it's a dynamic field, it might decay or change character over time, leading to entirely different cosmic futures. The accelerating universe also connects to fundamental questions about the nature of reality itself. Some theories suggest that our observable universe might be just one bubble in an infinite multiverse, where different regions have different values of the cosmological constant. In most regions, dark energy would be so strong that structures could never form, or so weak that the universe would have collapsed long ago. We find ourselves in a region where the value is just right for the existence of stars, galaxies, and life. This apparent fine-tuning of dark energy raises deep philosophical questions. Is our universe's hospitality to complexity just a cosmic coincidence, or does it reflect some deeper principle we don't yet understand? The discovery of cosmic acceleration has transformed these questions from philosophical speculation into empirical scientific problems. Future observations may help resolve the mystery of dark energy. Space-based telescopes designed to study billions of distant galaxies and map the large-scale structure of the universe, with unprecedented precision, may reveal whether dark energy is constant or evolving. Gravitational wave detectors might discover signatures of extra dimensions or modifications to gravity that could explain cosmic acceleration. The accelerating universe represents both humanity's greatest cosmological discovery and its deepest cosmic mystery. It reveals that we live in a universe whose ultimate fate is still being written by forces we don't understand, reminding us that even after centuries of scientific progress, the cosmos still holds profound secrets waiting to be discovered. Look up at the night sky, and you see what appears to be an eternal tableau of stars that have shone unchanged since the dawn of human history. Constellations that guided ancient navigators and inspired countless generations with their seemingly permanent beauty. But this apparent timelessness is an illusion created by the brevity of human lifespans compared to stellar evolution. Every star you see is dying, and their deaths will mark the end of the most luminous and active era in cosmic history. The universe is currently about 13.8 billion years old still, relatively young in cosmic terms. We live during what astronomers call the stelliferous era, when nuclear fusion in stellar cores illuminates the cosmos and drives the complex chemistry that makes planets and life possible. But this era of stellar brilliance is temporary, a brief, bright interlude in the much longer story of cosmic evolution. Stars are mortal because they depend on finite fuel supplies. Even the most massive stars, burning through their nuclear fuel at prodigious rates, live for only a few million years. Medium-sized stars like our Sun enjoy longer lives, about 10 billion years, but even they will eventually exhaust their fuel. The smallest stars, the red dwarfs, are the cosmic misers, burning so slowly that they can shine for trillions of years. But even they are not immortal. Our own Sun will begin its death throes in about 5 billion years. As it exhausts the hydrogen fuel in its core, it will start burning helium in a shell around the inert core, causing it to expand into a red giant star. The Sun will become so large that its outer layers will engulf the orbits of Mercury and Venus, and possibly Earth. The surface temperature will drop, giving the Sun a ruddy red appearance, but its enormous size will make it far more luminous than today. Eventually, the Sun will shed its outer layers entirely, creating a beautiful planetary nebular expanding shell of glowing gas surrounding the exposed core. This core, now a white dwarf star about the size of Earth but with the mass of the Sun, will be the final remnant of our stellar parent. It will shine not from nuclear fusion, but simply by radiating away its stored thermal energy over tens of billions of years. The most massive stars face more dramatic fates. When they exhaust their nuclear fuel, they collapse catastrophically and explode as supernovae, outshining entire galaxies for brief moments. Some leave behind neutron star objects so dense that a teaspoon would weigh as much as Mount Everest. Others collapse completely into black holes, creating regions of space-time so warped that not even light can escape. But regardless of how individual stars die, the overall trend is clear. The universe is gradually running out of fuel for star formation. Stars form from clouds of gas, primarily hydrogen, that collapse under their own gravity. But each stellar generation converts some of this hydrogen into heavier elements, and stellar deaths through stellar winds, planetary nebulae, and supernova explosions scatter these heavy elements through space, while often heating the surrounding gas too much for efficient star formation. Moreover, the accelerating expansion of the universe is gradually diluting the density of matter, making it harder for gas clouds to achieve the densities necessary for gravitational collapse. Fewer new stars are forming now than at any time in the past several billion years, and this trend will continue as available gas supplies dwindle. Computer simulations of cosmic evolution predict that star formation will essentially cease within about 1 trillion years. By that time, the universe will be about 100 times older than it is today, and the last generation of stars will be the long-lived red dwarfs, slowly burning their meager fuel supplies in an increasingly dark and empty cosmos. As the final stars exhaust their fuel and fade away, the universe will enter what cosmologists call the degenerate era. The primary sources of energy will no longer be nuclear fusion, but the slow cooling of white dwarfs, the gradual accretion of matter by black holes, and rare collisions between the dark remnants of dead stars. The cosmic background temperature will have dropped to nearly absolute zero, and the expansion of space will have separated most objects by vast distances. This stellar death sentence might seem depressing from our current perspective, but it's important to remember the timescales involved. The period from now until the last stars die spans a time interval 100 times longer than the current age of the universe. If the entire history of the cosmos, from the Big Bang to the present, were compressed into a single year, the remaining stellar era would last another century. For any civilizations that survive into this distant future, the challenge won't be a sudden catastrophe, but the gradual management of dwindling energy resources on cosmic timescales. They might harvest energy from the rotation of black holes, capture the fading light of dying stars, or even attempt to trigger new star formation by collecting and compressing the sparse matter scattered through space. The death of stars represents the closing of a chapter, but not necessarily the end of the cosmic story. In the incomprehensibly distant future, long after the last star has flickered out and the final black hole has evaporated, the universe will reach a state that physicists call maximum entropy heat, death of the cosmos. This isn't death by burning, but death by the ultimate triumph of thermodynamic equilibrium, where all energy has been distributed so evenly throughout space that no further work can be done, no more complexity can emerge, and time itself becomes meaningless. The concept of heat death emerges from the second law of thermodynamics, which states that entropy, roughly speaking, the measure of disorder in a system, always increases over time in isolated systems. The universe as a whole is the ultimate isolated system, and since the moment of the Big Bang, its total entropy has been steadily growing. Every process that occurs, from stellar fusion to the formation of galaxies to the evolution of life, increases the universe's overall disorder, even as it creates local pockets of organization. This might seem counterintuitive. After all, we see increasing complexity everywhere: stars forming from gas clouds, planets developing from stellar debris, life evolving from simple chemicals into conscious beings. But each of these organizing processes generates more disorder than order. Stars shine by converting organized matter into radiation, which disperses throughout space. Life maintains its organization by consuming energy and generating waste heat. Even thinking increases entropy as neurons burn glucose and release thermal energy. The timeline to heat death is staggering. After the last stars die in roughly 1 trillion years, the universe will be dominated by stellar remnants, white dwarfs, neutron stars, and black holes. These objects will slowly cool by radiating their thermal energy away, but the process will take unimaginably long. A white dwarf will take longer than the current age of the universe just to cool from white-hot to red-hot, and trillions of times longer still to approach the temperature of the cosmic background. Even black holes, which might seem eternal, are subject to entropy's inexorable march. Stephen Hawking showed that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly feebler. Black hole with the mass of our Sun would take longer than 67 years to completely evaporate. Black holes formed from stellar collapse will persist long after protons themselves begin to decay. Yes, even protons, the basic building blocks of atomic nuclear, may not be eternal. Some theories in particle physics predict that protons will eventually decay with half-lives of around 34 years. If true, this means that after about 40 years, essentially all ordinary matter will have disintegrated into electrons, positrons, neutrinos, and photons. The familiar atoms that make up stars, planets, and living beings will simply cease to exist. In this far future universe, the dominant objects will be black holes of various sizes, slowly evaporating in a sea of elementary particles and radiation. As the largest black holes finally disappear through Hawking radiation, they will briefly illuminate the cosmos with their death throes, before leaving behind only an expanding bath of photons, electrons, positrons, and neutrinos at an infinitesimally low temperature. Eventually, even this sparse collection of particles will be diluted by cosmic expansion until the average density of the universe approaches zero. Random quantum fluctuations might occasionally create brief patterns or even complex structures, but these would be exceedingly rare events in an overwhelmingly empty cosmos. In this state of maximum entropy, there would be no energy gradients to power processes, no temperature differences to drive heat engines, no organized structures to evolve or change. Time would continue to pass, but nothing would happen to mark its passage. The universe would have reached thermodynamic equilibrium, the ultimate fate predicted by the laws of physics as we understand them. Yet even this scenario contains uncertainties. Our understanding of dark energy, the nature of black hole information, and the ultimate fate of elementary particles remains incomplete. The heat-death scenario assumes that our current physical laws remain valid over these incomprehensible timescales, but new physics might intervene to provide alternative endings to the cosmic story. Even in the face of heat-death, the story of the universe might not truly end. At the frontiers of theoretical physics, scientists have proposed scenarios that could extend cosmic evolution far beyond the apparent thermodynamic finale, opening possibilities for renewal, transformation, or entirely new forms of existence that challenge our understanding of time, causality, and reality itself. One of the most intriguing possibilities involves quantum fluctuations in the vacuum of space. Even in the heat-death scenario, quantum mechanics tells us that space is never truly empty. Virtual particles constantly appear and disappear in fleeting quantum foam, and over vast timescales, these fluctuations could produce macroscopic effects. Given infinite time, quantum fluctuations could spontaneously assemble complex structures, including potentially entire universes. The mathematician and physicist Freeman Dyson calculated that quantum fluctuations could theoretically recreate any finite pattern, including exact copies of every human who ever lived given enough time. The timescales involved are beyond human comprehension. To randomly recreate a single human brain through quantum fluctuations might take 50 years. But in a truly infinite universe, even such improbable events become not just possible but inevitable. More dramatically, some theories suggest that quantum fluctuations could nucleate entirely new Big Bang events, creating bubble universes that expand within the dying cosmos. These new universes would have their own space-time, their own physical laws, and their own evolutionary histories. Our dying universe could become the parent of countless new cosmic offspring, each potentially developing its own stars, galaxies, and perhaps even life and consciousness. The concept of eternal inflation takes this idea even further. Some cosmological models propose that inflation, the rapid expansion that shaped our early universe, never truly ended but continues in some regions of a vast multiverse. In this scenario, what we call the heat death might only be the local fate of our particular cosmic bubble, while inflation continues to create new universes elsewhere in an infinite metacosmos. These new universes might have entirely different physical laws, different numbers of spatial dimensions, different fundamental constants, and different possibilities for complexity and life. Some might be sterile and simple, others might develop forms of organization and awareness that we cannot even imagine. The death of our universe would then be just one episode in an eternal cosmic story of birth, evolution, and renewal. Black hole physics offers another pathway beyond the apparent end. Some theories suggest that the information that falls into black holes is not destroyed, but encoded on their surfaces in a holographic form. When black holes eventually evaporate through Hawking radiation, this information might be released back into the cosmos, potentially allowing for the reconstruction of everything that ever existed. Even more speculatively, some physicists propose that the interior of black holes might contain entire universes with their own space-time dimensions. In this scenario, every black hole could be a cosmic womb, giving birth to new realms of existence that develop independently of their parent universe. The stellar mass black holes formed by dying stars and the supermassive black holes at galactic centers might each contain infinite worlds with their own histories and possibilities. The concept of time itself becomes problematic in these extreme scenarios. If the universe reaches a state of maximum entropy where no changes occur, does time continue to have meaning? Some physicists suggest that time might be emergent rather than fundamental, arising from the flow of information and the progression toward higher entropy. In a state of perfect equilibrium, time might effectively cease, making the universe's apparent death more like a transition to a timeless, eternal state. Quantum mechanics also raises profound questions about the nature of reality and observation. Some interpretations suggest that consciousness plays a fundamental role in determining physical reality through the measurement process. If this is true, then the existence of conscious observers might be necessary for the universe to have definite properties. The ultimate fate of consciousness itself becomes cosmologically significant in these scenarios. Advanced civilizations, if they survive long enough, might develop technologies that seem magical by current standards. They might learn to manipulate the quantum vacuum, engineer space-time itself, or even influence the fundamental constants of physics. Such beings might be able to prevent or reverse the heat death of their local cosmic region, creating islands of continuing evolution in an otherwise static universe. The concept of the omega point, proposed by physicist Frank Tipler, suggests that sufficiently advanced civilizations might be able to harness the gravitational energy of cosmic collapse to power unlimited computation, effectively achieving a form of technological immortality. Even if our universe is destined for heat death rather than collapse, similar principles might allow future beings to extract vast amounts of energy from black hole evaporation or other cosmic processes. Perhaps most remarkably, some theories in quantum gravity suggest that space and time themselves might be emergent properties of deeper, more fundamental structures. If true, then what we call the universe with its Big Bang origin and heat death conclusion might be just one particular manifestation of more basic underlying realities that exist beyond space and time as we understand them. These speculative possibilities remind us how much we still don't understand about the fundamental nature of reality. Our current physical theories, remarkable as they are, may represent only glimpses of a much deeper and more complex cosmic truth. The apparent finitude of our universe's future might reflect the limitations of our current knowledge rather than absolute constraints on cosmic possibilities. What seems certain is that any complete understanding of the universe's fate will require insights that go far beyond our current scientific knowledge. The questions raised by ultimate cosmic evolution about consciousness, time, causality, and existence push us toward the deepest philosophical and scientific frontiers. Even if our particular universe is destined to end in heat death, the possibility that existence itself might find ways to transcend apparent endings suggests that the cosmic story may be far from over. In contemplating these ultimate questions, We join a conversation that connects us to the deepest mysteries of existence and our place within the grand cosmic narrative. And so we reach the end of our journey through time, or perhaps the end of what we can currently know about cosmic evolution. From the first moment of creation to the speculative far future, we've traced an unbroken chain of cause and effect, spanning 13.8 billion years and extending into an almost unimaginable future. This is your story. The hydrogen in your DNA was forged in the first minutes after the Big Bang. The carbon in your proteins was assembled in stellar cores billions of years ago. The iron in your blood was scattered by supernova explosions before our solar system even existed. You are not just in the universe is in you, organized through 13.8 billion years of cosmic evolution into a pattern capable of consciousness and wonder. We stand at a remarkable moment in cosmic history. We exist after the universe has developed enough complexity for consciousness to emerge, yet before cosmic expansion has hidden the evidence of cosmic evolution from view. We are the universe becoming aware of itself, the cosmos developing the capacity for self-reflection. The future remains unwritten. Dark energy accelerates expansion, but we don't understand its nature. Stars will die, but quantum fluctuations might birth new realities. Heat death seems inevitable, but physics beyond our current knowledge might offer escape routes we cannot yet imagine. Whatever comes next, we are part of the grandest story ever told. The story of everything that was, is, and ever could be. As we close this cosmic chapter, I'm curious which era in the universe's history resonates most deeply with you. The violent beauty of the first stars igniting, the patient work of evolution crafting consciousness, or perhaps the mysterious far future that awaits. Share your thoughts in the comments below. If this journey through time has sparked your curiosity about our cosmic origins, I'd be honored if you'd subscribe and join our community of cosmic explorers. Each video we create is an invitation to see the universe through new eyes and appreciate the profound story we're all part of. The cosmos has many more secrets to reveal. Ready to discover what other mysteries await? Explore our complete collection of cosmic stories. Your next journey into the depths of space and time is just a click away.